Welcome to the deep dive. Today, we're going to be tackling some pretty abstract algebraic geometry.
Oh, yeah.
Specifically, the relationship between K-stability and rational points on Fano varieties.
So we've got a real treat for you.
Yeah.
This paper,
Who?
K-Stability of Pointless Del Pezzo Surfaces and Fano Three Folds by Audubon, Cheltsov, Kishimoto, and Mangolte.
Wow.
It goes deep, and I mean deep into some fascinating territory.
The title alone is enough to make your head spin, but
Right.
trust me, the insights here are worth the mental workout.
Now, you've got experience with this stuff. So, Fano varieties are these geometric objects with positive curvature, think spheres, but in higher dimensions.
Exactly.
And a big question is, do they have, rational points? Meaning, can we find solutions to their defining equations using, nice numbers like integers or fractions?
Exactly. And what this paper explores is the connection between the existence of those rational points and something called K-stability.
Okay.
Which is a way to measure how well-behaved a Fano variety is. Okay, let's unpack this K-stability a bit. It's a concept that pops up in various areas of geometry, and it's essentially a test to see if a Fano variety admits a special kind of metric
Right.
called a Kähler-Einstein metric.
Right. Those Kähler-Einstein metrics are really important for understanding the geometry of these spaces. If a Fano variety has one, it tells us a lot about its curvature and other geometric properties.
So in a way, K-stability is like a litmus test for niceness in the world of Fano varieties.
I like that analogy.
Yeah.
And what the authors do in this paper is show that if certain Fano varieties don't have a Kähler-Einstein metric, meaning they fail the K-stability test,
Right.
then they must have a rational point.
Hmm.
It's a surprising connection between geometry and number theory.
It really is. And it gets even more interesting when you consider that not all Fano varieties are created equal.
Right.
This paper specifically dives into Del Pezzo surfaces and Fano threefolds,
Right.
which are kind of like the poster children for these objects.
They're classic examples, and they exhibit a lot of the interesting behavior that makes this whole area of research so rich. Del Pezzo surfaces are two-dimensional, and they can have what are called quotient singularities,
Okay.
which are like mild irregularities.
Okay, for our listeners who might not be as familiar with those, imagine taking a perfectly smooth surface and pinching it at a point.
Okay.
That pinch creates a singularity, a point where the surface is no longer smooth. Quotient singularities are a specific type of singularity that arises from certain group actions, and they're considered mild because they don't disrupt the geometry too drastically.
Exactly. And one of the key results in this paper, Theorem A, focuses on these Del Pezzo surfaces with, at most, quotient singularities. It states that if such a surface doesn't admit a Kähler-Einstein metric, then it must have a rational point.
That's a pretty powerful statement.
Yeah.
It's saying that if the geometry is a bit off, then you're guaranteed to find a solution to the equations defining the surface using nice rational numbers.
Right. And the proof of Theorem A is quite intricate. The authors utilize a lot of sophisticated machinery, including the minimal model program and techniques from birational geometry. They essentially show that if a Del Pezzo surface with at most quotient singularities doesn't have a Kähler-Einstein metric, then you can perform a series of geometric transformations called birational modifications to arrive at a surface that does have a rational point.
So they're essentially manipulating the geometry to force the existence of a rational point.
That's a good way to put it. And one of the things that makes this result so interesting is that it doesn't tell us anything about where that rational point might be or how many there might be.
Right.
It just guarantees that at least one exists.
It's like a mathematical treasure hunt where you're told there's treasure buried somewhere, but you have no map to guide you.
Exactly. And to make things even more interesting, the authors provide a counterexample showing that the rational points guaranteed by Theorem A don't have to be smooth. A smooth rational point would mean that the solution corresponds to a nice, well-behaved point on the surface.
Right. It's possible to have a rational point that corresponds to a singular point on the surface.
Yes.
Which can make things a bit trickier to analyze.
Absolutely. So Theorem A gives us this tantalizing link between K-stability and the existence of rational points, but it also leaves us with some intriguing open questions.
It's like the paper is opening up new avenues of exploration rather than providing all the answers.
Exactly. And that's what makes this area of research so exciting. There's still so much we don't know.
Right.
And each new discovery leads to even more questions.
Now, after delving into these Del Pezzo surfaces, the paper moves on to Fano threefolds, which are the three-dimensional counterparts.
And this is where things start to get really interesting.
Okay.
While Theorem A provided a pretty clear-cut result for surfaces, things become more nuanced in 3 dimensions.
Right, because with an extra dimension, there's more room for complexity.
Exactly. And what the authors discover is that even if a Fano threefold fails the K-stability test, meaning it doesn't have a Kähler-Einstein metric, it might still be what they call pointless.
Pointless, meaning it has absolutely no rational points. That seems to contradict what we saw with Theorem A.
It does seem counterintuitive.
Yeah.
But remember, Theorem A only applied to surfaces with, at most, quotient singularities. In 3 dimensions, things can get more complicated.
Right.
And there are Fano threefolds that don't have any rational points, even though they don't admit a Kähler-Einstein metric.
So it's like the connection between K-stability and rational points starts to break down in higher dimensions.
In a way, yes. But the authors don't just leave it at that. They go on to prove another remarkable result, Theorem B, which provides a complete classification of these pointless Fano threefolds.
So they're essentially saying, okay, there are exceptions to the rule, but here's a precise list of all the possible exceptions.
Exactly. And this classification is a major accomplishment. Yeah.
It tells us precisely which Fano threefolds can be pointless, and it turns out that there are only a finite number of possibilities.
That's incredible. They've managed to pin down these elusive, pointless threefolds.
And the proof of Theorem B is a real tour de force. They combine a wide range of techniques, including tools from the minimal model program, Mori theory, and the theory of algebraic groups.
It sounds like they pulled out all the stops to get this result.
They did. And what's remarkable is that the classification is quite explicit.
Oh, wow.
They give a detailed list of all the possible cases, including their defining equations and specific properties.
So if you're working with a Fano threefold and you're wondering if it might be pointless, you can just consult this list and see if it matches any of the known cases.
Exactly. Theorem B provides a powerful tool for anyone working in this area. Now, after establishing these 2 major theorems, the paper goes on to delve into a series of specific examples to illustrate their findings.
Right.
And these examples aren't just random cases they pulled out of a hat.
No, they're not.
They're carefully chosen to highlight the different ways in which K-stability and rational points can interact in the world of Fano threefolds.
Exactly.
They're like little case studies that bring the abstract theory to life.
Exactly. And some of these examples get pretty wild, involving exotic objects like G2 torsors and hyperelliptic curves.
Okay, you're going to have to explain those terms to me. They sound like something out of science fiction.
Well, a G2 torsor is a geometric object that's related to a special type of group called an exceptional Lie group.
Okay.
And a hyperelliptic curve is a generalization of an elliptic curve, which you might be familiar with from cryptography.
Okay, those are definitely not terms you hear every day. But it sounds like these examples are really pushing the boundaries of what we know about Fano varieties.
They are, and the fact that the authors are able to construct these concrete examples shows just how deep their understanding of this subject is.
It's like they're speaking a different language, the language of advanced algebraic geometry.
They are. And the beauty of it is that even if we don't fully understand all the technical details, we can still appreciate the elegance and ingenuity of their work.
It's like admiring a work of art, even if you're not an art expert.
Exactly. There's a certain beauty to the way these mathematicians are able to manipulate abstract concepts and create these intricate mathematical structures.
Now, before we dive into the specific examples, I want to take a step back and connect this back to our listeners.
Okay.
Why should someone who's not a mathematician care about K-stability and rational points on Fano varieties?
That's a great question.
Yeah.
And there are actually a few reasons why this research is relevant beyond the world of pure mathematics. First of all, Fano varieties appear naturally in many areas of physics, particularly in string theory.
Okay.
They play a role in understanding the geometry of Calabi-Yau manifolds,
Right.
which are thought to be the fundamental building blocks of our universe.
So these seemingly abstract objects might actually hold clues about the nature of reality itself.
Exactly. And the existence of rational points on these varieties can have implications for the types of physical phenomena that are possible. It's a bit like saying that the shape of a drum determines the sounds it can produce.
That's a great analogy. So understanding the geometry of these objects could help physicists make predictions about the universe.
Right. And another reason why this research is important is that it has connections to number theory, particularly the study of Diophantine equations, which are polynomial equations where the solutions are restricted to integers.
Oh, those are the equations that Fermat's last theorem is all about.
Exactly. And Fano varieties provide a geometric framework for studying certain types of Diophantine equations.
Okay.
Finding rational points on these varieties can sometimes lead to solutions to these equations, which can have applications in cryptography and coding theory.
So this seemingly abstract research could have practical applications in areas that affect our daily lives.
It's true. And the fact that there are connections between these different areas of mathematics is part of what makes this field so fascinating.
Yeah.
It's like discovering hidden pathways between seemingly unrelated worlds.
It's like the universe is speaking to us through the language of mathematics.
I love that way of putting it. And the more we learn about this language, the more we uncover about the universe and ourselves.
Okay, I think we've laid a good foundation for understanding the significance of this research. Now, are you ready to dive into some of those intriguing examples?
Absolutely.
Okay, let's start with example 6.1, which delves into these mysterious G2 torsors.
Okay.
What exactly are those, and how do they relate to pointless Fano threefolds?
Well, before we jump into G2 torsors, let's revisit homogeneous spaces as they form the backdrop for this example. Imagine a space where every point looks the same, like a perfectly smooth sphere where you can't tell one point from another just by looking locally.
Right.
That's the essence of a homogeneous space. Mathematically, it's represented as GP, where G is a Lie group and P is a subgroup.
Okay, so we're talking about spaces with the high degree of symmetry.
Right.
And how do these G2 torsors come into play?
Now, a G2 torsor is a specific type of geometric object that's associated with a particular exceptional Lie group, denoted as G2. Think of it as a bundle over our homogeneous space, GP, but with a special twist.
Okay.
This bundle carries the structure of G2, and that structure dictates how we can move from one point in the bundle to another.
It sounds incredibly abstract. How does this connect back to our Fano varieties and rational points?
Here's where it gets really fascinating. Example 6.1 focuses on a specific five-dimensional homogeneous space, which, for simplicity, we'll call X.
Okay.
This X is a G2P space.
Okay.
And the authors show that there's a unique, pointless version of X called a Q-form. This pointless Q-form, let's call it X, is constructed using a specific G2 torsor over X.
Wait, so we're taking this abstract G2 torsor, using it to twist our original space X, and somehow ending up with a pointless version.
That's the gist of it. And what makes this construction even more remarkable is that the G2 torsor they use is defined by a very specific element in something called Milnor-K theory.
Okay.
It's denoted as 1, Nasha 1, Nasha 1. And it's like a secret code that unlocks this particular pointless construction.
It's like a hidden key in the mathematical universe leading to this unique object. But we're still dealing with a five-dimensional space.
Right.
How do we get back to our Fano threefolds?
That's where the magic of geometry comes in. The authors show that you can slice this five-dimensional pointless Q-form, X, in a very specific way to obtain a three-dimensional Fano variety.
Okay.
This slicing is done using something called a divisor, which is like a hypersurface within X. And the resulting three-dimensional shape, amazingly, is a pointless Q-form of a smooth Fano threefold belonging to family number 1.9.
So by understanding this special G2 torsor and taking a precise slice of this twisted five-dimensional space, we end up with a concrete example of a pointless Fano threefold.
Right.
It's like a mathematical magic trick.
It really is. Yeah. And this example highlights the power of these abstract tools like G2 torsors and Milnor-K theory.
Right.
They allow us to create and understand objects that would otherwise be incredibly difficult to grasp.
It's like opening up a new dimension of mathematical understanding.
Exactly. And this is just one of many fascinating examples the authors explore in this paper.
Okay.
Each one offers a unique glimpse into the intricate interplay between K-stability and rational points.
This is incredible. We're going to have to pause here for now, but don't worry, we'll be back soon to continue our deep dive into the world of pointless Fano threefolds. Welcome back to the deep dive. We're continuing our exploration of K-stability of pointless del Pezzo surfaces in Fano threefolds by Aben, Chalza, Kishimoto, and Mangolte, and we've just scratched the surface of these mind-boggling pointless Fano threefolds.
And believe me, there's a whole lot more to uncover. Where we left off, we had just delved into the fascinating world of G2 torsors and how they can be used to construct these elusive, pointless objects.
Right. Using a G2 torsor and some clever slicing, they managed to create a pointless Fano threefold belonging to family number 1.9. It's amazing how these seemingly abstract tools can lead to such concrete results.
It speaks to the power of mathematics to bridge the gap between the abstract and the concrete. And the examples just keep getting more intriguing.
Okay, I'm ready for more. What's next on our pointless adventure?
Let's move on to example 6.2. This one explores pointless Fano three-folds defined over the real numbers,
Okay.
specifically those that are prime.
Prime, meaning they can't be obtained by slicing a higher dimensional Fano variety.
Exactly. They're like the fundamental building blocks of pointless Fano three-folds over the real numbers.
Okay.
And what's particularly interesting is that the paper highlights a whole family of these prime pointless Fano three-folds belonging to family number 1.10.
So we're not just talking about isolated examples. There's a whole class of these objects out there.
Right.
That's incredible.
It highlights the richness and diversity of these pointless constructions. Now ready for some more surgery on cubic shapes.
Always. I'm picturing those beautifully curved surfaces defined by third-degree equations. What do they do with those?
Example 6.3 takes us back to the world of cubic three-folds. The paper points out that there are pointless cubic three-folds defined over the rational numbers.
Okay.
Meaning there are cubics out there with no rational solutions at all.
Wait, no rational solutions? That seems counterintuitive. Aren't cubics supposed to have at least one?
Not necessarily. And to illustrate this, they construct a specific example.
Okay.
They start with one of these pointless cubics and slice it along a specific curve.
Another example of mathematical surgery. What kind of curve do they use?
They intersect the cubic with a two-dimensional linear subspace,
Okay.
resulting in a smooth curve. Then, by blowing up the cubic along this curve, a technique we've encountered before they obtain a new shape.
And this new shape is?
A pointless Fano threefold belonging to family number 2.5. So by strategically slicing a pointless cubic, they create a new pointless object in a different family.
It's like a mathematical chain reaction of pointlessness.
Right.
What's next?
Example 6.4 takes us back to the realm of real numbers, focusing on pointless Fano threefolds in family number 2.10. They use a technique where they intersect a smooth cubic threefold defined over the real numbers with a codimension 2 linear subspace.
So they're essentially taking a slice of a cubic, but this time they're specifically working over the real numbers.
Exactly. And the key here is that the cubic threefold they start with has no real points. This ensures that when they take the slice and blow it up, the resulting Fano threefold also has no real points.
It's like they're starting with a special ingredient to guarantee a specific outcome.
Right.
I'm beginning to see a pattern here.
You're catching on. Now, example 6.5 is less about a specific construction and more of a pointer. The authors direct us to another paper that provides explicit constructions of pointless Fano threefolds over the real numbers, specifically those belonging to family number 2.12.
So it's like a treasure map leading to a whole trove of pointless examples.
Exactly. And speaking of treasures, example 6.6 introduces another fascinating player, hyperelliptic curves.
Okay, hyperelliptic curves. Those are a special type of algebraic curve, right?
Yes. Think of them as generalizations of elliptic curves, which are famous for their use in cryptography. And in this example, they start with a specific pointless hyperelliptic curve defined over the real numbers.
Good.
The curve is of genus 2,
Right.
which is a measure of its complexity.
Okay.
Then they cleverly embed this curve into a pointless quadric threefold.
Quadric threefold. Those are shapes defined by second-degree equations.
You're right. Think of things like spheres and ellipsoids, but in 3 dimensions.
Okay.
And they specifically choose a quadric threefold that has no real points.
So they're taking a curve and placing it inside a higher dimensional shape,
Right.
both of which are already pointless.
Exactly. And the key is that when they blow up the quadric along this embedded curve, the resulting Fano threefold also has no real points.
It's like a nesting doll of pointless objects. What family does this Fano threefold belong to?
This one falls into family number 2.13, expanding our collection of pointless examples even further.
Okay, on to example 6.7. This one sounds familiar. They're using G2 torsors again, aren't they?
You've got a sharp eye. It does use a similar idea to example 6.1, but in a different context. This time, it focuses on a 4-dimensional space called a Mukai fourfold of genus 10.
Okay.
And just like with the 5-dimensional space in example 6.1,
Right.
there's a unique pointless Q form of this Mukai fourfold that can be constructed using a certain G2 torsor.
So another example of a hidden key leading to a pointless construction. I'm starting to see the versatility of these G2 torsors.
They're quite powerful tools, and just like before, we can slice this pointless Q form to obtain a three-dimensional Fano variety.
Okay.
The resulting shape is a pointless Q form of a smooth Fano threefold belonging to family number 2.16.
So we've now used this G2 torsor technique to construct pointless examples in two different Fano threefold families.
Right.
That's pretty remarkable.
It highlights the interconnectedness of these seemingly different geometric objects. And speaking of connections, let's move on to example 6.8, which brings us back to pointless Fano threefolds over the real numbers.
Okay, this time focusing on family no 2.19.
Back to real numbers. I'm curious to see what they do here.
This example involves a smooth quadric threefold defined over the real numbers.
Okay.
They intersect it with a hyperplane,
Right.
which essentially means taking a slice of the quadric to create a surface.
Okay, so we're taking the slice of a quadric to create a surface.
Right.
Sounds familiar.
But here's the clever part.
Right.
They choose the quadric and the hyperplane in such a way that the resulting surface has no real points.
Sneaky. So they're starting with a pointless object and then slicing it to create another pointless object.
Exactly. And by blowing up this surface at a specific point, we obtain a pointless Fano threefold belonging to family number 2.19.
Another precise surgical procedure in the world of mathematics. And what about example 6.9? Does that build on this idea?
You guessed it. Example 6.9 provides a concrete illustration of the construction in example 6.8 using specific equations.
Okay.
They use a quadric defined by the equation by 2 plus y2 plus z2 plus t2 equals 0.
Ah, so they're giving us a tangible example to ground those abstract concepts.
I always appreciate that.
This specific quadric has no real solutions.
Right.
And by carefully choosing a hyperplane, they ensure that the resulting surface, and consequently the Fano threefold, also has no real solution.
It's great to see how those abstract ideas translate into concrete equations.
Yes.
What's up next on our pointless journey?
Example 6.90 focuses on pointless Fano threefolds over the real numbers belonging to family number 2.20.
Okay.
They start with, you guessed it, a pointless smooth quadric threefold defined over the real numbers, and then blow it up along a smooth rational curve.
Another blow up.
Yeah.
But this time they're using a curve. What kind of curve are we talking about?
In this case, they use a curve of genus 0, which means it's essentially a twisted version of a circle.
So they're taking a circle-like curve and using it to modify a pointless quadric.
Right.
I'm picturing a mathematical potter shaping clay on a wheel.
And just like a skilled potter, they choose this curve in a way that guarantees the resulting Fano threefold will also have no real points.
It's a delicate dance of shapes and equations to create a pointless outcome. Do they give us a concrete example for this one too?
Of course. Example 6.11 illustrates the construction in example 6.10 using those concrete equations we both love. They use the same quadric from example 6.9, defined by the equation by 2 plus y2 plus z2 plus t2 plus 002. Then they choose a curve defined by specific parametric equations, ensuring it lies within this pointless quadric.
So by plugging in those parametric equations, we can see exactly how this curve fits within the pointless quadric and leads to a pointless Fano threefold.
Precisely. It brings those abstract concepts to life. Okay, ready for another pointless creation?
Absolutely. Lay it on me.
Example 6.12 explores another pointless Fano threefold over the real numbers.
Okay.
They start with, you guessed it, a pointless smooth quadric threefold defined over the real numbers. However, this time, instead of blowing it up along a curve, they blow it up along a conic.
Hold on. A conic, that's a specific type of curve, right?
Yes. A conic is a curve defined by a second-degree equation. Think of familiar shapes like circles, ellipses, and parabolas.
Ah, so they're taking one of those classic curves and using it to modify a pointless quadric. I'm seeing a theme here.
You're spot on, and just like in previous examples, they choose this conic carefully to ensure that the resulting Fano threefold inherits the property of being pointless.
It seems like the choice of curve is crucial in these constructions.
Absolutely. The geometry of the curve plays a key role in determining whether the resulting Fano threefold will have real points or not.
So it's a delicate interplay between the curve and the quadric. What about example 6.13? Does that provide more concrete details?
Exactly. Example 6.13 illustrates the construction in example 6.12 with, you guessed it, equations. They use our trusty pointless quadric defined by the equation by 2 plus y2 plus z02 plus t2 plus t2 equals 0.
Right.
And they choose a specific conic that lies within this quadric.
Okay.
By blowing up the quadric along this conic, we obtain a pointless Fano threefold belonging to family number 2.22.
It's amazing how they can tweak these equations to create different pointless objects.
It truly is. Now, example 6.14 takes a slightly different approach.
Okay.
Instead of starting with a quadric threefold, this example starts with a del Pezzo surface of degree 5.
Del Pezzo surfaces, we talked about those earlier. They're those special surfaces with a certain type of positive curvature, right?
Yes.
And some of them can be pointless too.
You remember well.
Yeah.
In this example, they start with a pointless del Pezzo surface of degree 5 defined over the real numbers, and then blow it up along a specific elliptic curve.
Elliptic curves. Those are curves defined by a special type of cubic equation, right? The ones with deep connections to number theory and cryptography.
That's right. And by carefully choosing this elliptic curve, they ensure that the resulting Fano threefold also has no real points.
It's like they're weaving a tapestry of pointless objects using curves as their threads.
A beautifully poetic way to put it. Now, example 6.15 explores pointless Fano threefolds in family number 3.0, and they use a technique we've seen before, blowing up a quadric threefold, but this time there's a twist.
Okay, I'm intrigued. What's the twist?
They blow it up along not one, but two conics. And they choose these two conics very carefully to ensure that they're disjoint, meaning they don't intersect each other.
So it's like performing two separate surgeries,
right,
each using a different conic.
Exactly.
What's the outcome of this double blow-up?
The combination of these two blow-ups results in a pointless Fano threefold belonging to family number 3.1.
It's a symphony of blow-ups, each playing its part to create a pointless masterpiece. What about example 6.16? Does that also involve multiple blow-ups?
It does. Example 6.16 also starts with a pointless smooth quadric threefold.
Right.
But this time, instead of directly blowing it up along curves, they first create a specific configuration of curves within the quadric.
Okay, how do they do that?
They intersect the quadric with two carefully chosen surfaces.
Okay.
These surfaces are defined by equations that ensure the intersection is a combination of a twisted line and a smooth rational curve.
So they're setting the stage for pointless construction by creating this specific arrangement of curves.
Exactly. And the key is that they choose these surfaces so that both the twisted line and the smooth rational curve are pointless over the real numbers.
Okay.
Then they find another twisted line that doesn't intersect the smooth rational curve.
Okay.
Finally, they blow up the quadric threefold along both this new twisted line and the original smooth rational curve.
So it's a two-step blow-up process.
Yes.
Using two different types of curves. That's impressive.
And the result of this intricate dance is a pointless Fano threefold belonging to family number 3.1.
It's a carefully choreographed sequence of steps, all leading to a pointless finale. This paper is full of surprises.
It truly is a testament to the creativity of mathematicians. And speaking of surprises, example 6.17 introduces a new twist, literally by bringing in complex numbers.
Complex numbers. Okay, this is getting interesting.
They start with a specific pointless smooth quadric threefold defined over the real number.
Okay.
This quadric is given by the equation by 2 plus y2 plus z2 plus t2 plus w2 equals 0.
That equation looks familiar.
Yes.
We've seen variations of it before.
It's a classic example of a pointless quadric.
Right.
Now, they intersect this quadric with a hyperplane,
right,
just like in some previous examples. This intersection results in a surface.
So another slice of a pointless quadric. What's so special about this particular slice?
This surface contains two special lines that are conjugate to each other over the complex numbers.
Okay.
These lines are defined by the equations w, x, I, y, z, it, and w, x, I, y, z, x equals I, y, z equals it, where I is the imaginary unit.
So they're using complex numbers to define these lines. But how can lines defined by complex numbers exist on a surface that's supposed to be over the real numbers?
That's the clever part. While each line individually involves complex numbers, their combination is actually defined over the real numbers. It's like a hidden symmetry within the complex realm that manifests in the real world.
That's fascinating. So what do they do with these special lines?
They blow up the quadric threefold along these two lines.
Another blow up, but this time using these special conjugate lines.
Exactly. This blow up creates a new shape, which they then transform further using a birational transformation.
Birational transformation. Those are transformations that preserve certain geometric properties while changing the shape, right?
You're right. It's like giving the object a mathematical makeover while keeping its essential character intact.
So what's the result of this makeover?
The result is a new three-dimensional shape.
Okay.
which is a Fano threefold.
Okay.
And if we look at its complex version,
Right.
it's a divisor of degree 11(1) in the space P2x P2, or P2 is the complex projective plane.
Okay, I'm following so far. They took this object, gave it a makeover, and now its complex version has this specific property. What do they do next?
They take this new Fano threefold and blow it up along a specific smooth curve.
Okay.
This curve is chosen so that its complex version is isomorphic to a conic in P2.
Another strategic blow-up using a conic. It seems like conics are playing a recurring role in these constructions.
They are quite versatile, and the result of this final blow-up is a pointless Fano threefold defined over the real numbers. Its complex version belongs to family number 3.13.
Wow, that was quite a journey. We started with a pointless quadric and went through a series of blow-ups and transformations to arrive at a pointless Fano threefold in a different family.
It highlights the interconnectedness of these different geometric objects. Even though they might seem distinct at first glance, there are often hidden pathways connecting them.
I'm starting to appreciate the intricate web of relationships within this field of mathematics.
We're only just beginning to unravel its complexities, ready for another adventure with pointless objects.
Bring it on. I'm eager to see what other mathematical marvels await us in this paper.
Okay, example 6.18 takes us to a slightly more abstract realm. They construct a pointless Fano threefold over the real numbers by working with the product of pointless conics.
Pointless conics. Those are the curves defined by equations like by 2 plus y2 equals 0,
Yes.
which have no real solutions, right?
Exactly. They start by taking the product of two pointless conics, denoted by C. This creates a four-dimensional object, Q, which is essentially a pair of conics.
So it's like a double dose of pointless curves living together in a four-dimensional space.
Precisely. Then they consider a divisor Z inside Q, which is essentially a three-dimensional slice of this four-dimensional object.
Okay.
The complex version of this divisor, denoted by ZC, has a specific degree on QC, which is the complex version of Q.
Okay, so we're taking a three-dimensional slice of this double conic object.
Right.
What do they do with this slice?
They create another object,
Yeah.
S, by taking the product of this divisor, Z, with a pointless conic. This new object, S, also has a complex version, SC, which turns out to be isomorphic to the product of the complex versions of Z and C.
So we're building up more complex objects by taking products of these pointless objects. It's like a mathematical construction set.
And they use the properties of these objects to deduce that Z must be isomorphic to C. Essentially, they leverage the fact that these objects are pointless to infer a specific relationship between them.
That's clever. They're using the absence of solutions to reveal underlying structural connections. What happens next in this construction?
They introduce another divisor, D, within S. And they consider its complex version, DC, which has a specific degree on the complex version of S. Then they define a curve, B, as a general member of a specific linear system associated with D, and the canonical divisor of Z.
Okay, I'm following so far. They're using divisors in linear systems to construct this curve. What's the significance of this curve, B?
This curve, B, is designed so that its complex version, BC, intersects the complex version of S in a specific way. In particular, the image of BC under a projection map is a conic in the complex projective plane.
So they're manipulating these objects to create specific configurations in the complex world. What's the ultimate goal of this construction?
The goal is to create a pointless Fano threefold. They achieve this by taking the product of Q with a pointless conic, resulting in a six-dimensional object. Then they consider a specific divisor within this six-dimensional object. This divisor is defined in a way that relates to the previously constructed objects. And its complex version is a smooth Fano threefold belonging to family number 4.13.
Wow, that was a whirlwind of constructions. We started with pointless conics, moved up to 4 and 6 dimensions, and ended up with a pointless Fano threefold. It's like a mathematical odyssey through different dimensions.
It's a testament to the ingenuity of mathematicians in using abstract tools to create these intricate pointless objects.
Okay, we've seen quite a few examples now, each highlighting a different approach to constructing these pointless Fano threefolds. What's the overall takeaway from all these examples?
The examples showcase the richness and complexity of the relationship between case stability and the existence of rational points. They demonstrate that while a lack of case stability often implies the existence of rational points, there are intriguing exceptions, and these exceptions can be constructed using a variety of methods.
It's like a mathematical puzzle. where the pieces can fit together in unexpected ways, and the authors are showing us just how diverse and creative those solutions can be.
That's a great analogy. Each of these examples offers a unique glimpse into the subtle interplay between geometry and algebra, revealing a world of unexpected connections and surprising results.
This is fascinating stuff, but I think we'll need a pause here for now.
Yeah.
Don't worry, we'll be back soon to wrap up our deep dive into the world of pointless Fano threefolds. Welcome back to the deep dive. We've been on quite a journey exploring the world of pointless Fano threefold, guided by this incredible paper by Aban, Cheltsov, Kishimoto, and Mangolte.
It's been a whirlwind tour of G2 torsors, blow-ups, and conics, all carefully orchestrated to create these fascinating objects that defy expectations.
You know, going through all these examples, it really strikes me how creative mathematicians can be.
Oh, yeah.
It's like they're artists,
yeah,
but their canvas is the abstract realm of mathematics.
I love that analogy.
Yeah.
They're using these powerful tools and techniques to sculpt these intricate shapes and uncover hidden relationships.
And speaking of hidden relationships, I'm curious about the broader implications of this research.
Yeah.
We've talked about how Fano varieties appear in physics and have connections to number theory.
Right.
But what are some of the specific ways in which this understanding of case stability and rational points could impact those fields?
Well, in physics, the existence of rational points on Fano varieties can have implications for the types of solutions that are possible in certain physical models.
Okay.
For example, in string theory, Fano varieties play a role in describing the compactification of extra dimensions.
Right.
The presence or absence of rational points on these varieties can affect the properties of the resulting four-dimensional spacetime.
So it's like the geometry of these objects is influencing the physics of our universe.
Exactly. And understanding which Fano varieties have rational points and which ones don't can help physicists narrow down the possibilities and make more precise predictions.
That's incredible. And what about number theory? How does this research connect to that field?
One way is through the study of Diophantine equations, which are polynomial equations where the solutions are restricted to integers. Fano varieties provide a geometric framework for understanding certain types of Diophantine equations.
Yeah.
Finding rational points on a Fano variety can sometimes lead to finding integer solutions to a corresponding Diophantine equation.
So it's like the geometry is guiding us towards solutions in the realm of numbers.
Precisely. And this connection has potential applications in cryptography and coding theory, where finding integer solutions to certain equations is crucial.
So this research is not just an abstract pursuit. It has the potential to impact fields with real-world applications.
And that's one of the things I find so exciting about mathematics.
Yeah.
Even the most abstract ideas can have unexpected connections to the world around us.
Now, before we wrap up, I want to touch on something we discussed earlier.
Okay.
The fact that some Fano threefolds are inherently pointless.
Right.
While others are guaranteed to have rational points if they fail the case stability test.
Right. Theorem B provided that incredible classification of those special pointless cases.
Right.
Those exceptions to the general rule.
Exactly. And that classification raises an interesting question for me. Why are those exceptions so important? What do they tell us about the relationship between geometry and number theory?
They challenge our intuition about how those two fields are connected.
Yeah.
We might expect that a lack of niceness in the geometry, meaning a failure of case stability, would always lead to the existence of rational points.
Right.
But these exceptions show us that the relationship is more subtle than that.
So it's like those pointless Fano threefolds are revealing a deeper level of complexity in the interplay between geometry and number theory.
Exactly. And that's what makes them so intriguing.
Yeah.
They're pushing us to refine our understanding of these fundamental mathematical concepts.
It's like they're forcing us to dig deeper and ask more profound questions.
And that's what drives mathematical progress.
Yeah.
We encounter these unexpected results,
right,
and they challenge us to develop new tools and perspectives to explain them.
Well, I think we've given our listeners a lot to ponder today.
I think so.
We've journeyed through abstract dimensions, encountered exotic objects, and uncovered hidden connections.
Absolutely.
And hopefully they're leaving with a sense of awe at the beauty and depth of mathematics.
Absolutely.
So until our next deep dive, keep those brains buzzing. All right. Welcome back, everyone, for another deep dive. Today we're going to be tackling a pretty fascinating area of math, where geometry and algebra, they come together, you know.
Yeah.
It's all about case stability and how it connects to rational points on Fano varieties.
Yeah, that's right. And we've got quite the stack of papers here.
We do. By Aben, Cheltsov,
Kishimoto,
and Mengelte.
Uh,
Ready for us to break down. And, just a heads up, we're going to be getting into some seriously cool math here, but I think our listeners are ready for it.
Absolutely. And since we know everyone here is well-versed in algebraic geometry, we can just dive right into the good stuff, the heart of their findings. No need to mess around.
Yeah, sounds good to me. But before we get totally lost in all the theorems and all that,
sure.
How about we just set the stage a little bit? What is K-stability?
Yeah.
What are rational points?
Yeah.
And how do they relate to Fano varieties?
Right. Okay, so why don't we start with Fano varieties? So these are geometric objects, and they're defined by very specific algebraic equations. They have some really cool curvature properties.
Yeah.
One way to think about them is to imagine a sphere, right?
Okay.
It's a space that's like positively curved.
Okay, I'm picturing a sphere. Got it.
Okay, good.
What about rational points?
Yeah.
What do those have to do with our curved space?
Oh, that's a great question. So imagine picking points on that sphere, but here's the catch. All the coordinates of these points, they have to be fractions, like nice, clean fractions.
Okay.
So instead of some crazy decimal, pi,
right.
You would have 1/2 or -3/4, things like that.
Okay, I see. So we've got our Fano variety. It's all curved. We've got these special points with the nice fraction coordinates. Where does K-stability fit into all this?
Okay, so K-stability, it's a little more abstract, but basically it's like a way to measure how stable the geometry of our variety is. So imagine you're trying to stretch a perfectly smooth elastic film over the surface of our sphere. Right? If you can do that, stretch it without any wrinkles or tears.
Okay.
You could say that sphere is stable, geometrically stable.
Okay.
That's kind of what K-stability is getting at. The existence of a special kind of metric. It's called a Kähler-Einstein metric.
Right.
And this metric, it fits perfectly on the variety.
Okay, so it's like how smoothly can we dress our Fano variety, right?
Yeah.
I'm starting to get it, but this is where things get really interesting. Because the papers we're looking at today, they explore a surprising connection.
Yeah.
They found that if a Fano variety doesn't have rational points, it might tell us something about its K-stability.
Exactly. And the authors, they go deep into this connection, right, especially for Fano varieties of dimensions 2 and 3.
Okay.
And what's really cool is that this relationship can even be used to prove that rational points exist in some cases.
Now, that's what I call a plot twist.
Okay.
Let's unpack these results. Where do they even start?
They start with the two-dimensional case. So that would be del Pezzo surfaces, which are a specific kind of Fano variety. Their theorem A, it states that, if you have a del Pezzo surface with, at worst, what are called quotient singularities, defined over a subfield of the complex numbers, and it doesn't have what we call a Kähler-Einstein metric, then it must have a rational point defined over that subfield.
Hold on. Let's break that down a bit. Quotient singularities. What are those exactly?
Okay, so imagine you have a smooth surface, right?
Okay.
And you're kind of folding it onto itself at certain points.
Okay.
You create a little crease or a cone-shaped point.
Okay, yeah, I can picture that.
Yeah.
So this theorem's saying that if we can't smoothly dress our del Pezzo surface with that special metric, right?
Yeah.
It has to have at least one point with those fractional coordinates. That seems kind of counterintuitive.
It does, doesn't it?
Yeah.
It's the lack of a Kähler-Einstein metric means there's some sort of obstruction in the geometry.
Okay.
And that forces the existence of a rational point.
Interesting.
And you know what? They give us an example.
Oh, I love a good example. Hit me.
Okay, so consider the surface. Defined by the equation, and this is going to sound a little mathy, but stick with me. Sex by dollars plus by 22 plus by 32 equals ever dollars.
Okay.
This surface, it's known to be K-unstable, so no Kähler-Einstein metric.
Okay.
And the only rational point it has over the rational numbers is the singular point, and that is 0.0.1.
So even a singular point where it's all pinched can be a rational point.
Absolutely. Because remember, it just means its coordinates can be written as fractions.
Right.
Yeah, it doesn't matter what's going on, at the point itself on the surface, just the coordinates.
Okay, so we've covered the two-dimensional case.
Yeah.
What happens when we go up a dimension, to the Fano three-folds?
Yeah.
Does it get more complicated?
It does get a little bit more complex, as you might expect.
Yeah.
The relationship between K-stability and rational points, it isn't as clear-cut. But that's okay. That's what Theorem B is for. It helps us understand that complexity.
So does the same basic idea still hold? Like, no smooth film. Means there's got to be a rational point.
So not necessarily. Theorem B, it shows us that a Fano threefold, it might not have a rational point, even if it doesn't have a Kähler-Einstein metric.
Wait, really? So what are some of the cases where the film doesn't fit, but we still don't have those nice fractional coordinate points?
Okay, well, the paper, it gives us a few pretty fascinating examples. One is when the Fano threefold is constructed as, and I'll try to say this slowly, Segel sysiskel C times F11, or $6 C times S7, where $C is a pointless conic.
A pointless conic? That sounds almost like a contradiction.
I know, right? So basically it means the specific type of curve, this conic, it doesn't have any rational points over the field we're working with.
Okay.
And then you take the product of this conic with some other surfaces, like the Fano surface $1 or the del Pezzo surface $7 zizels. And what you get can also end up without rational points, even if it's not k-stable.
So we're building these threefolds from parts that are already kind of missing rational points. So it makes sense that the final product might also be missing them.
Exactly.
Okay. Are there any other exceptions?
There are. The authors, they present 8 specific examples where a Fano threefold, it can be k-unstable, but it might still not have rational points. These are pretty complex examples. They involve some really interesting geometric constructions.
Can you give me a taste of one of those constructions?
Okay, so one that's visually pretty striking is the blow-up of a pointless quadric in Math BBP4 along a quartic elliptic curve.
Okay, I might need a little help visualizing that one. Blow up, what's that mean geometrically?
Okay, so imagine our pointless quadric. It's a surface, right? Living in 4-dimensional projective space.
Okay.
Now focus on a specific curve on its surface. A blow-up is like we're inflating that curve, replacing it with a higher dimensional sort of tube-like structure.
Okay, so we're strategically injecting some extra dimensions into our quadric.
Yeah, exactly.
Got it.
And even with that change, the resulting threefold might still not have any rational points, even if it's not k-stable.
These exceptions are pretty cool. They show just how nuanced this connection is in higher dimensions.
Yeah, definitely.
Is there anything else Theorem B tells us?
Yes. It also gives us a really neat corollary.
Okay.
It says that any smooth Fano threefold that has a what's called a strictly k-semi-stable geometric model, it has to have rational points.
Okay, strictly k-semi-stable. Is that like almost k-stable?
Yeah, you got it. It's a slightly weaker condition. Think of it this way. K-stable is like a perfectly smooth film, right? Strictly k-semi-stable is like, it might have some tiny wrinkles, but it still essentially fits.
Right.
And k-unstable is like the film is all bunched up and it doesn't cover the surface properly.
I like that analogy. So even with these like almost smooth varieties, we're still guaranteed to find rational points.
Exactly. It's another clue that these two concepts are really intertwined.
This is all super fascinating. So Theorem B helps us understand these exceptions in higher dimensions. But let's zoom out for a sec.
Yeah.
How do we even categorize Fano threefolds in general?
Okay, so mathematicians, they've actually systematically classified Fano threefolds into numbered families based on their geometric properties.
So it's like we're organizing them into different species.
Exactly. And within these families, there are 2 key categories that are relevant to our discussion.
Okay, break it down for me. What are the categories?
Okay, so the first category, it's families where every smooth member, no exceptions, has a rational point.
Okay.
So for example, we've got families O2.9, O2.11, O2.14, O2.17, O2.20, O2.8, and O3.8, and O2.11. They all fall into this category.
So if you pick any smooth Fano threefold from those families,
Yeah.
you know for sure you'll find at least one rational point.
Yep.
That's pretty cool. What about the second category?
Okay, so the second category, it's a little more interesting. These families, they might have some members that don't have rational points. The rebels, right. But here's the catch. Those pointless members, they are always k-ball stable.
So even if they don't have those fractional coordinate points, they've still got that perfectly smooth film.
Exactly. And some examples of these families are families U1.9, U1.10, U2.5,
Okay.
and a few others. This classification, it's really important because it helps to solidify that link between k-stability and rational points.
I'm seeing a pattern here. even when things get more complicated in higher dimensions, there's still this underlying connection between these two ideas that like they're dancing around each other, sometimes in sync, sometimes not, but always connected.
That's a beautiful way to put it. It really does show you the deep symmetries and connections that exist in math.
So my brain is buzzing with all these theorems and families.
Sure.
But how about we take a closer look at their methods? How do they prove these results?
Okay, so the paper, it uses some pretty high-level proof strategies. But let's focus on two of the key approaches. So the first one is called the Evans-Wong method. It uses delta invariance to analyze the K-stability of a variety.
Delta invariance. Sounds a little intimidating. What are those all about?
Well, they're essentially measures of how far a variety deviates from being K-stable. So imagine you've got a scale that tells you how wonky the film on our variety is. Calculating these invariants, it involves some pretty serious math, like complex integrals and having to consider a lot of different geometric cases.
I can see why you need some serious math chops for that. What about the other technique?
Okay, the other technique involves analyzing what are called minimal model programs.
Okay.
And this is all about simplifying complex geometric objects, but in a way that preserves their key properties. So it makes it easier to figure out whether rational points exist or not.
So it's like decluttering the geometric landscape so we can see things more clearly?
Exactly.
I love how these math tools can be visualized so intuitively. Can you give me an example of how they use these techniques in the paper?
Okay, so let's look at example 6.1.
Okay.
They construct something called a pointless Q-form of a Fano threefold.
Okay.
That's in family year 1.9.
Okay.
And they do this by cleverly intersecting two divisors within a 5-dimensional space. And through a series of geometric arguments, they prove that this particular threefold, it has no rational points.
Wow. Constructing something out of nothing, or I guess proving the absence of something.
Exactly.
Are there other examples where they use these techniques?
Absolutely. Example 6.8, it shows us the construction of a pointless real Fano threefold. And this one is obtained by blowing up a pointless quadric.
Okay.
They carefully walk us through the steps. And they explain why this threefold, it doesn't have real points.
So they're giving us concrete examples to show how these abstract theorems actually work.
Exactly. They're not just throwing equations at us.
Right.
They're grounding the arguments in tangible geometric objects.
This has been a really amazing overview of K-stability and rational points. I could already see how connected these two ideas are.
Yeah. And we're just getting started. There's a lot more to explore in the world of Fano varieties.
I'm excited to dive in.
Me too. So as we go deeper into the paper, we're going to see how the authors really highlight specific Fano threefold families, and they show us how K-stability and rational points, they do this dance. It's a very intricate dance.
Yeah, I'm excited to see these families up close. So which one do they start with?
Okay, so they begin with family 1.9. Remember, this is one of those families where you can have members without rational points, but those members, they always have to be K-polystable. And the challenge here, the real goal, is to prove that this is always true. For any Fano threefold that belongs to this family, if it doesn't have rational points, it's got to be K-polystable.
Yeah, it's like a proof by contradiction.
Yeah.
We're going to say, okay, what if there is a pointless member that's not K-polystable?
Yeah.
And then see if that leads us to some kind of problem.
Exactly. That's exactly right. So the proof starts by assuming, okay, we have this Fano threefold, we'll call it $6, and it has no K-positional points. And dollars is just the field we're working over. We also assume that its geometric model, which we'll call $6, is not K-polystable. And this means that there exists a special divisor, we'll call it $5 over $6, that computes what we call the delta invariant.
Delta invariant, that rings a bell. That's how we measure how far away a threefold is from being K-stable.
Yeah, you got it. Think of it like a gauge that tells us how wonky or how wrinkled our film is, right?
Right.
And since we're assuming $6 is not K-polystable, it's delta invariant, it's got to be less than or equal to 1.
Okay, so we've got our wonky Fano threefold here. We're trying to find a contradiction. What's the next step?
Okay, so because $X is not K-polystable, this divisor $5, we can think of it as being defined over our field dollars. This lets us look at the center of this divisor on our original threefold. We'll call the center $. And $, it can't be a surface because of how this Fano family is structured, its properties.
So what is Z-line? Is it like a point or a line Or some other weird curve?
It has to be a curve. Remember, we're saying that sinus dollars has no rational points.
Right.
So Zeeler, it can't be a point that's defined over dollars.
Okay.
And it can't be a surface. So the only thing left is that it has to be a curve.
Ah, so we've narrowed things down. We've got this mysterious curve, Zeeler. What do we do with it?
Now, we use that Abon-Swang method that we were talking about earlier.
Okay.
And it involves looking at the delta invariant, but not just for the whole threefold.
Okay.
We're going to be looking at it locally. Our round points on this curve, Zeeler lore.
So we're zooming in, looking for those wonky spots on the curve.
Exactly. And the really cool thing about this method is that it gives us very precise lower bounds for these local delta invariants.
Okay, so those lower bounds, they're going to help us find our contradiction.
Yes, they are. So by analyzing these bounds and using the fact that Zellers is defined over tellers, they show that those local delta invariants, they have to be strictly greater than 1.
Hold on. Wait a minute. Didn't we say earlier that the overall delta invariant had to be less than or equal to 1?
We did. That's right.
Because we're assuming $6 is not K-polystable.
Exactly. And that's the problem. That's our contradiction.
Right.
If those local delta invariants around points on Zeeler are all greater than 1, well, then the overall delta invariant for the whole threefold, it can't be less than or equal to 1.
So our initial assumption that we could have this pointless member of family O 1.9 that's not K-polystable, that just doesn't work.
Exactly. It falls apart. So that's how they prove that any pointless member of family UN 1.9, it's got to be K-polystable.
Okay, that's amazing. So one family down, how many more to go?
Well, quite a few. The paper continues, and it applies similar strategies to lots of other families, like family 1.10, family 202.2, family 2.12, lots of numbers.
Lots of numbers.
But each proof has its own, unique little twists and turns. But the main idea, the main principle, it stays the same. We're going to assume there are no rational points, and we're going to use that to find a contradiction with the case stability properties.
Yeah, I can see how that might start to feel repetitive, even if there are different details each time.
Sure.
Can we maybe walk through one more proof, something that maybe highlights a specific challenge or a unique aspect of these proofs?
Of course. Why don't we look at family U 2.99?
Okay.
This one's really interesting because it has a more complex geometric construction.
Okay, more complexity. I'm intrigued. What's so special about this family?
Okay, so here, our Fano threefold $6. It's constructed by using what we call blow-ups. Remember those?
Yeah.
We're expanding, using balloons.
Right. The balloon expansions.
Exactly. So we start with a pointless form of Mach BBP3, blow up a particular curve on it, and then we blow up another curve on the space that we get after the first blow-up.
So we're inflating curves within curves. This is getting pretty wild.
Yeah, it gets pretty abstract. So the goal is to prove, again, that if this threefold has no rational points, then its geometric model has to be K-polystable. So we start the proof the same way as before. We assume that the geometric model, it's not K-polystable, which means there's got to be that wonky divisor, $5, and we'll call it centered on $60.
Okay, I think I'm starting to get the hang of this. So $6 can't be a point because we're assuming $6 has no points.
Right.
But it can't be a surface either.
Exactly. The tricky thing with this family is that Ziga dollars could potentially be contained inside a very special surface in $6. And we'll call this surface Kähler's, and it's related to how we did all those blow-ups. It's essentially a lifted version of a quadric surface.
Okay, so we've got this lifted surface, $6. Where do we go from there?
So the authors, they very carefully analyzed this possibility. Could Ziga dollars be inside Kähler's? And they use the Abon-Swang method to estimate those local delta invariants around points in that intersection.
So zooming in on those potential problem areas.
Exactly. And what they find is a contradiction by looking very closely at how Zia and Q intersect. And using the lower bounds that the Abon-Swang method gives us, they show that the local delta invariants around points in that intersection, they have to be bigger than 1. Strictly greater than 1.
But that doesn't make sense, right?
It doesn't.
We were assuming the overall delta invariant was less than or equal to 1?
That's right. And that means that ZL cannot be completely contained inside the surface.
What is ZL? Just wandering around this threefold all on its own.
Pretty much. And that leads us to the next step in the proof, which is to show that Zue has to be what we call a geometrically rational curve.
Okay.
Which means that the shape of Zia, we can describe it using rational functions. It's not too crazy complicated, geometrically speaking.
Okay, so we've tamed our wild curve, ZL dollars. How do we use this to get to our final contradiction?
Now that we know that Zilai is a rational curve and it's not trapped inside that surface Kähler, we can use the Abon-Swang method again. But this time, we look at the entire curve, zilli, not just where it might intersect with Kähler.
So more delta invariant calculations, but now we have a better understanding of zilli.
Exactly. And once again, we find a contradiction. They show that if our assumptions were true, then the delta invariant associated with zilli, it would have to be both greater than and less than 1.
Wow, that's impossible.
Exactly. So our initial assumption that we could have this threefold with no rational points and also not k-polystable, it falls apart.
Wow. So that's how they prove that for family U2219, any member that doesn't have rational points, it has to be k-polystable.
Exactly. You got it.
This is incredible. The level of detail, it's like watching a master watchmaker putting together this incredibly complicated timepiece.
I know. It's really beautiful, isn't it? And each family has its own unique little challenges. The fact that they have to come up with all these different arguments, it just shows you how rich algebraic geometry really is.
Yeah, it's making me really appreciate just how vast and complex this area of math is.
And we've only just scratched the surface. There's so much more to explore.
So we've explored these proofs, showing that for some of these Tempo threefold families, if they don't have rational points, they've got to be k-polystable. But I always like seeing, actual examples. Did they give us any of those in the paper?
Oh, yeah, they do. In section 6, they actually show us how to construct specific pointless, smooth Fano threefolds, so we can really see these theorems in action.
Excellent. I'm ready for some geometric eye candy.
Yeah.
What kind of cool objects are we talking about here?
Okay, so one that really stands out is example 6.1, where they construct a pointless Q-form of a Fano threefold from family U1.9. And they do this by intersecting two special divisors within a 5-dimensional space.
A Q-form, what exactly does that mean?
Right. So basically it means that this variety, it's defined over the rational numbers.
Okay.
So all the coefficients in its equations, they're just fractions.
Yeah.
And what's really cool is that this particular Q-form, it's also what's called a G22 torsor, which means it has a very specific kind of symmetry. It's related to this thing called the exceptional Lie group G222.
Okay, I think I'm getting a little lost in the weeds here.
Sure.
Do they have any examples that are maybe a little more down to earth?
Yeah, definitely. So example 6.2, it's a bit more familiar. They give us a family of smooth Fano threefolds. And these are defined over the real numbers, the ones we use every day.
Okay.
But here's the thing. They don't have any real points.
Wait, no real points? But these threefolds, they're made using real numbers, right?
Right.
How can they not have any points that are real numbers?
Yeah, it's kind of a mind bender.
It is.
But it's possible. Because remember, we're talking about complex geometric objects, and they don't necessarily have to behave the way we expect real numbers to.
Okay, that's pretty wild. I'm seeing how these examples are really challenging our intuition about geometry. Are there any other cool constructions?
Yeah, there are a bunch. So example 6.3 is a classic. They start with a smooth cubic threefold in Math BP44 that has no rational points, which is already pretty cool.
Okay.
And then they blow up a curve on it. And the threefold that they get, it's from family O2.5.
Okay.
And it ends up also not having rational points, just like the cubic it came from.
So it's like the no rational points trait is being passed down.
Exactly.
Inherited. Okay.
Yeah. And they use a bunch of other techniques, too. Like they've got examples with real Fano threefolds. Those are in family O2.2 fold. They use constructions with hyperelliptic curves and quadric threefolds. Those are in family O2.3. And even a threefold that comes from blowing up a quadric along two conics. That one's in family O2.2.
I'm noticing a lot of these involve blowing things up.
Blowing up is super useful. It lets you create new varieties with really specific properties. It's a key tool in algebraic geometry.
So these examples, they're not just, fun little side notes.
Right.
They're actually showing us how those abstract theorems work in specific cases.
Exactly. They're like the proof, right? The evidence that all these connections between k-stability and rational points and this wild world of Fano varieties, it's all real.
This has been such an awesome journey.
Yeah.
Into higher math. Are there any big takeaways or any questions that have come up for you while we've been doing this deep dive?
One thing that's been on my mind is how important the field we're working over is to the geometry. We've seen pointless Fano varieties, and they're defined over the rational numbers, the real numbers, even some more unusual fields. And it makes me think, how does the geometry of these varieties, how's it connected to the algebra of the field itself?
It's like every time we answer a question in math, it just leads to more questions. That's what makes it so cool.
Absolutely.
Well, I think we've successfully navigated this pretty complex mathematical terrain.
We did it.
Thanks to your expert guidance.
Oh, it's been a pleasure.
It really has been a pleasure exploring these groundbreaking results with you. And to everyone listening, until next time, stay curious. Welcome back to the show. Today we're taking a deep dive into Fano varieties.
Oh, nice.
And specifically, some really cool results about the existence of rational points on these varieties.
Okay.
And how they connect to the existence of Kähler-Einstein metrics on their geometric models.
Interesting.
Now, I know you're all experts in algebraic geometry, so we can skip the basic definitions and just get right into the good stuff.
Let's do it.
So to start unpacking this whole thing, let's look at Del Pezzo surfaces.
Yeah, okay.
Theorem A in this paper is the one that really caught my eye.
Yeah.
It says that if you have a Del Pezzo surface defined over a subfield K of the complex numbers, and it doesn't have any K rational points,
right,
then its geometric model has to have what's called an orbifold Kähler-Einstein metric. So it's almost like saying that the absence of something is forcing a geometric property.
That's a really good way to put it. It is kind of counterintuitive when you first think about it. This idea that the absence of rational points, which are basically solutions to equations within our field, say, is telling us something about the curvature of the geometric model. It's a really cool example of how these arithmetic properties can influence the geometry.
And to make things a little more concrete, they actually give a specific example.
Oh, nice.
They use the surface S, which is defined by this equation, x5 plus xsurface plus x equals 0. And this is in Pia law. And this is a degree 8 Del Pezzo surface over the rational numbers.
Okay.
And this example, it really highlights that sometimes the only rational points you might end up with are just the singular points.
Which makes sense.
So that kind of leads us nicely into the world of Fano threefolds.
Okay.
As might expect, things get a bit trickier in higher dimensions.
Yeah.
Even when you're dealing with smooth Fano threefolds, if the geometric model doesn't have a Kähler-Einstein metric, that doesn't automatically mean that they're going to be Kähler-rational points.
Right, right.
And they even throw in some curveballs, like the examples C cross R and C cross S, where C is a pointless conic.
Oh, yeah, I remember those.
I was a little confused about why those are considered exceptions.
Yeah, so those examples are kind of clever because they're exploiting a loophole.
Okay.
The conic C itself doesn't have any K rational points. And then that property gets inherited by the entire product.
Right.
But then theorem B comes in to save the day. It tells us exactly what the exceptions are.
Gotcha.
It defines the very limited set of situations where you have a smooth Fano threefold that's defined over K.
Okay.
And doesn't have a Kähler-Einstein metric on its geometric model,
right,
but might still not have any K rational points.
So it's saying that these loophole cases are pretty rare.
Exactly.
But it goes even further than that and actually lists out what the exceptions are.
Oh, wow.
Yeah. So it outlines these 8 different cases.
Interesting.
And they're all pretty intricate, involving blow-ups along these specific curves. But what's interesting is that the geometric models of all of these exceptions end up being K unstable. So that kind of hints at a deeper connection between this idea of K stability and the existence of rational points.
That makes sense.
Yeah, so it's not just a random list of exceptions. There's this underlying theme of K instability going on.
That's cool.
And then corollary 1.1 really emphasizes the importance of K stability.
Okay.
Because it says, if you have a smooth Fano threefold over K, and it has a strictly K semi-stable geometric model, then it has to have K rational points.
Wow.
No exceptions.
So that's a pretty strong result.
Yeah, it's a pretty powerful statement.
Yeah.
And what's even cooler is that they actually show us
that
pointless forms of these 8 exceptions actually exist.
Oh, wow.
Over a lot of different subfields of the complex numbers. They even provide constructions over the real numbers.
That's really interesting.
Yeah, so these aren't just like theoretical possibilities.
Right.
They actually have these concrete realizations.
Yeah, it really brings the math to life.
Yeah, it really shows you how deep and rich this connection is.
Definitely.
Between the arithmetic and the geometry.
For sure.
Now, if you're ready to go a little deeper,
I'm ready.
We can start looking at how they actually prove all these really cool results.
Okay.
They use a really clever combination of geometric intuition and these powerful algebraic tools.
Sounds good.
So it's worth taking a closer look at how they put it all together.
Yeah, I'd love to see that.
I'm especially interested in how they use the valuative criterion for case stability and things like the invariant and Zariski decomposition. It's like they're assembling this all-star team of mathematical concepts.
Yeah, that's a good way to think about it.
To really tackle this problem.
So how do they actually do it?
So one of the main strategies they use is to start by assuming the opposite of what they're trying to prove.
Okay.
So they assume that the geometric model is not k-polystable. And then they use the valuative criterion to find this special prime divisor where this instability is like concentrated.
Gotcha.
It's almost like setting a trap.
Yeah.
You assume the opposite,
right,
and then the whole argument kind of falls apart.
I like that.
And the tools they use to spring the trap are pretty impressive.
Yeah.
Let's take a closer look at how they handle Fano threefolds in family 02.13.
Okay.
It's in lemma 5.6.
Okay.
They start by assuming that a Fano threefold, we'll call it X in this family, doesn't have any k rational points. And they want to prove that its geometric model, which we'll call XC, has to be k-polystable.
So it's like a proof by contradiction.
Exactly.
Nice.
So what's the next move?
I'm curious.
Well, they use the fact that XC comes from blowing up a smooth quadric threefold, we'll call that QC, along a smooth curve C. Now, by applying some pretty powerful tools, like lemma 2.5, they show that the conic bundle structure of XC actually descends down to K. So that means that the conic bundle is defined over our base field, not just over the complex numbers.
Right.
So they're kind of bringing the problem down to earth a bit.
That makes sense.
Yeah.
So what happens next?
Now they focus on the curve Z,
Okay.
which is where this potential K instability is concentrated.
Gotcha.
There are two possibilities.
Okay.
Either Z is a fiber of the conic bundle, or its image is a curve in P.
Right. So they're narrowing things down.
Exactly.
Yeah.
And in both of these cases, they construct this special del Pezzo surface S that contains a point of Z. Now here comes the really clever part.
What's that?
They use what's called the Abban-Swan method to get a lower bound on the Foudin variant at that point.
Interesting.
Now remember, the Don variant kind of tells us how stable a Fano variety is.
Right.
So a lower value means it's less stable.
Okay.
Now, because they assume that XC is not k-polystable, the Don variant at any point on Z, including this one in S, can't be bigger than 1.
Okay.
But then they look really carefully at the geometry of S.
Right.
And use some really powerful tools like the Zariski decomposition, and they get a lower bound that's actually bigger than 1.
Oh, wow.
So that's our contradiction. It's like this carefully constructed del Pezzo surface is acting like a magnifying glass. And it reveals that the threefold is actually stable.
Wow, what a clever approach.
It's pretty amazing.
Yeah.
And they use a similar strategy with a few modifications to prove the k-poly stability of pointless Fano threefolds in several other families.
So they kind of have this general framework.
Yeah, exactly.
That's really neat.
It's amazing how they can combine this geometric intuition with these really sophisticated algebraic techniques.
It is pretty cool.
I'm starting to see how elegant and deep this area of research is.
Me too.
And we've really only just scratched the surface.
Yeah, for sure.
There's still so much more to explore.
Absolutely.
Like those concrete examples of these Fano threefolds.
Right.
But maybe we should take a break here. And let everything sink in a bit.
Sounds good.
What are your first impressions of this connection between rational points and k-stability?
I mean, I'm finding it fascinating, this whole idea that whether or not there are rational points can actually determine the geometric structure of these varieties is pretty mind-blowing.
It's crazy, right?
And the way they use all these advanced tools to prove these results is super impressive.
I know.
I'm definitely eager to learn more about these exceptional cases and see some concrete examples.
Yeah, me too.
That'll be cool.
All right, let's take a moment to gather our thoughts.
Okay.
And then we'll dive into the next part of this mathematical adventure.
Sounds good.
So before the break, we were talking about how they use that valuative criterion and stuff like the Ein invariant to prove the k-poly stability of some of these Fano threefolds.
Yeah, it's like they're detectives or something.
Right.
Using these math tools to like uncover these hidden geometric truths.
It's really cool.
It's like putting together a puzzle where like each theorem and lemma is a piece.
Yeah.
And it all leads to the bigger picture.
Speaking of the bigger picture, you mentioned concrete examples.
Yes.
Section 6 of the paper actually has some really interesting constructions in it.
It's one thing to prove theorems you know?
Right.
But it's so cool to actually see these like abstract objects come to life.
Yeah.
With specific examples.
It makes it so much more real.
Exactly.
So what kind of examples did they give?
Well, they have a bunch that show just how diverse and complex these pointless, smooth Fano threefolds can be.
Right.
Like, for example, they construct a pointless form of a smooth Fano threefold in family 1.9. And the construction uses this really cool interplay between the exceptional group G2 and octonion multiplication.
Really?
Yeah, it's a beautiful example of how different areas of math can come together in these unexpected ways.
That's what I love about math.
Me too.
You find these connections and you're like, wow,
I never would have thought of that.
like you're discovering these hidden pathways between different mathematical landscapes.
Totally.
So are there any other examples?
Yeah, they also give some examples over the real numbers.
Okay.
Which are maybe a little easier to visualize.
Right.
For instance, they construct a pointless smooth Fano threefold in family or 3.10.
Okay.
And they use a pointless real smooth quadric threefold for that one. And some carefully chosen linear subspaces.
So even these familiar geometric objects can have these hidden depths.
Exactly.
That's pretty amazing.
Now, going back to those 8 exceptional cases in Theorem B, you mentioned that they're all K unstable.
Yeah.
Why is that?
Yeah, what is it about those specific cases that makes them break the general rule?
That's a great question. It gets to the heart of what makes these exceptions so interesting.
Yeah.
Let's look closer at the first one. Okay. It's the blow-up of a pointless quadric in Poe along a quartic elliptic curve. Now, a quadric in Poe, it's defined by a homogeneous polynomial of degree 2.
Right.
And when we blow it up along a curve, we're basically replacing that curve with a copy of Poe at every point.
So we're adding in this new geometric structure by doing this blow up.
And the curve that we choose to blow up along, that plays a really important role.
Okay.
In this case, it's a quartic elliptic curve.
Right.
So that means it's defined by a polynomial of degree 4, and it has this special shape, like a torus.
So the geometry of that curve is contributing to the K instability of the threefold.
Exactly. It turns out that when you have the quadric, the blow-up, and the specific geometry of that elliptic curve all together, they create a situation where that valuative criterion for K-stability, it fails.
Oh, interesting.
We can find a divisor that destabilizes it. It kind of pulls the geometry away from being K-stable.
It's like the elliptic curve is a weak spot in the geometry.
Yeah, you could say that.
Makes it unstable.
And I'm guessing the other 7 exceptions, they also have these subtle geometric things going on that make them K unstable.
That makes sense.
It's all about these specific combinations, blow-ups, base varieties, and curves. And in each case, it's the interaction between those elements that leads to the K-stability criterion failing.
It's amazing how these complicated geometric constructions can have such a big impact on whether something's stable or not.
It really shows how deep and interconnected algebraic geometry is.
For sure.
Even small changes in the construction can make a huge difference.
Absolutely.
Now, I know you're a big fan of Del Pezzo surfaces.
Oh, yeah.
How do they fit into all of this? This whole picture of K-stability and rational points.
Well, Del Pezzo surfaces are really interesting.
They are.
They have a long history and connections to all sorts of areas of math.
It's true.
Remember, a Del Pezzo surface is a smooth projective surface with an ample anticanonical divisor.
Right, and their classification is really elegant.
Exactly.
The degree of the surface is super important.
And in terms of K-stability, Del Pezzo surfaces are actually pretty well behaved. A smooth Del Pezzo surface is always K-stable.
Oh, wow.
And that stability is related to their geometric properties.
In what way?
Well, for instance, they have Kähler-Einstein metrics.
So you could say they're the good guys of the Fano family.
Yeah, kind of.
When it comes to K-stability.
Exactly.
And they're often used as building blocks for constructing and understanding more complicated Fano varieties.
Right, like that special Del Pezzo surface we used earlier to get that contradiction in the proof.
In Lemma 5.6, that's a perfect example of how you can use them strategically to understand the K-stability of these higher dimensional Fano varieties.
It's like they're the keystones holding everything together.
That's a good analogy.
It's really fascinating to see all these connections in this area of math.
And there's still so much we don't know.
Oh, yeah.
Like the exact relationship between the case stability of a Fano variety
Right.
and the existence of rational points in higher dimensions.
Yeah, there's definitely a lot more to discover.
Absolutely.
But maybe we should pause here again.
Okay.
And give everyone a chance to process all this information.
Sounds good.
We've covered a lot of ground.
Yeah, we have.
From those 8 exceptions to the role of del Pezzo surfaces in understanding case stability.
Take a moment to think about what we've discussed.
Yeah.
What stood out to you? What new questions popped up?
Okay.
We'll be back soon to wrap things up.
Yeah.
With some final thoughts and a challenge for you to ponder.
All right. We're back for the final part of our deep dive into Fano varieties. We've gone through a lot of theorems and explored some really interesting cases. I think we're starting to get a good grasp of this connection between rational points and case stability.
It's been a great exploration. I think the main takeaway from this paper is this surprising link between rational points and Kähler-Einstein metrics.
Yeah, especially when we're talking about Fano varieties.
Right. We saw how if there aren't any k-rational points, a lot of times that means the geometric model has to have a Kähler-Einstein metric.
And those exceptions we talked about, they really highlight how deep this connection is.
Exactly. They make you think about the little details of the geometry that can make something stable or unstable.
So as we wrap up, what do you think is the biggest thing we've learned from all this?
I think the most important thing is that the absence of rational points can have a big impact on the geometry of these Fano varieties.
Yeah, and the authors actually leave us with a really interesting question at the end.
What's that?
They ask if we could find even more connections to case stability. If we look at the k-rational points of Fano varieties in even higher dimensions.
That's a great question. It makes you want to keep exploring and see what else is out there.
It's like they've given us this map to a whole new mathematical world.
Yeah, and who knows what we'll find there.
Well, it's been great diving into this topic with you.
Likewise.
And for our listeners, we hope you've enjoyed this exploration of Fano varieties. And until next time, keep those mathematical minds working. Welcome back to the deep dive. Today, we're going deep into pointless Fano varieties. And we're going to assume you already know the basics, so no basic recap today. We're diving right into the advanced stuff.
Yes. Today we're focusing on varieties over a subfield K of the complex numbers, more specifically the ones without any k-rational points, the so-called pointless varieties.
Pointless varieties, huh? Sounds a bit bleak, but I bet there's more to it than meets the eye, right?
You bet. The absence of k-rational points is surprisingly connected to another concept in complex geometry, Kähler-Einstein metrics.
Kähler-Einstein metrics. I vaguely remember those from grad school, but refresh my memory.
Simply put, a Kähler-Einstein metric is a special type of metric on a complex manifold. It's like a fingerprint that reveals a lot about the manifold's geometry. And the fascinating thing is for Fano varieties, having a Kähler-Einstein metric often means not having certain rational points.
So the existence of one thing implies the lack of another. That's a cool connection.
Exactly. And that's what we'll be exploring today. We have a stack of research papers filled with theorems, proofs, and examples all about this relation.
All right, let's unpack this then. First up, del Pezzo surfaces, specifically those with quotient singularities.
Okay, so theorem A of this paper says that a del Pezzo surface over K with, at worst, quotient singularities has to have a k-rational point if it doesn't have an orbifold Kähler-Einstein metric.
So if our del Pezzo surface over K is missing this specific metric, we're guaranteed to find at least one k-rational point on it. That's pretty strong.
It is. And to illustrate this, the paper gives a classic example. The surface x euros plus x exarios. This surface is pointless over the rational numbers, no rational points. But its complex model does have a Kähler-Einstein metric.
Great example. But isn't there a little nuance here? Can't a pointless surface still have singular points defined over K?
That's a sharp observation. The theorem doesn't guarantee smooth k-rational points, just that there are some k-rational points even if they're singularities.
Okay, so in 2 dimensions, these Fano orbifolds over K without a Kähler-Einstein metric always have k-rational points. What happens in higher dimensions?
Things get trickier. Moving up to Fano threefolds, the relationship gets much more complex. The paper lays this out in Theorem B.
Okay, what does Theorem B say about pointless Fano threefolds?
Theorem B states that if you have a smooth Fano threefold defined over K, and its geometric model isn't Kähler-Einstein, then it generally has a k-rational point.
So the general idea is similar to the Pezzo surfaces. No fancy metric means there's a point. But you said generally. Are there exceptions?
Yes, and this is where it gets interesting. There are 8 specific cases where a pointless Fano threefold might not have a Kähler-Einstein metric.
8 exceptions. Okay, can you give us some examples of these rule breakers?
Sure. 2 of the more straightforward examples involve a pointless conic C where CK is empty. We have CX-F1 and CX-S where S is a K-form of S7.
So taking a pointless conic and creating a product with certain Fano varieties can lead to these exceptions. What about the other 6 cases?
The paper dives into those in detail, but let's focus on the first 3 that can be constructed even over the real numbers. The first one is the blowup of a pointless quadric in paro along a quartic elliptic curve.
So we're taking a pointless quadric, already interesting, and blowing it up along a specific type of curve. What about the second exception?
The second exception is a double cover of pair x pair ramified along a surface of bidegree 284.
Double covers and ramification. We're definitely getting more abstract here. And the third?
The third is the blowup of pair along a curve whose complex model is a disjoint union of a line and a smooth rational curve of degree 7.
Okay, so we have these 8 exceptions, each with its own unique construction and properties. What's the key takeaway?
All 8 of these exceptions are what we call K-unstable, which brings us to another important concept, K-stability.
K-stability, right. Yeah. So now we have pointless varieties, Kähler-Einstein metrics, and K-stability. How are they all connected?
Think of K-stability as a finer tool that determines whether a Fano variety can even have a Kähler-Einstein metric. It goes beyond just the existence or non-existence we talked about earlier.
So K-stability is like a more sensitive test for the possibility of a Kähler-Einstein metric. And these 8 exceptions fail this test.
Exactly. They're all K-unstable, meaning they can't have a Kähler-Einstein metric. This is highlighted in corollary 1.1 of the paper, which says that smooth Fano threefolds with strictly K-semistable complex models always have K-rational points.
That means if a smooth Fano threefold passes even a weaker K-stability test, it has to have a K-rational point. That's powerful.
It is. It shows how intertwined these concepts are. The absence of rational points, Kähler-Einstein metrics, K-stability, they're all part of the same geometric puzzle.
Now, the paper mentions the Iskovsky-Mori-Mukai classification. What's that about?
The Iskovsky-Mori-Mukai classification is a way to group Fano threefolds into families based on their traits, and this paper systematically analyzes these different families in relation to our topic.
So it's a way to categorize these Fano threefolds. What kind of families are we looking at?
There are 2 main types connected to Theorem B. The first type are families where every member, if defined over K, will always have K-rational points.
So no matter how you construct a Fano threefold in these families, as long as it's over K, it will always have K-rational points. And the second type?
The second type are families where the pointless members, those without K-rational points, are actually K-polystable.
K-polystable. That sounds like a strong form of K-stability. What does it mean here?
K-polystability is crucial for the existence of a Kähler-Einstein metric. So these families have pointless members that might have those special metrics.
Okay, so we've categorized Fano threefolds into families, some always having K-rational points, others possibly having Kähler-Einstein metrics. But how do we prove these connections? I imagine the paper is full of complex proofs.
It is, and it uses some clever techniques. The proofs often use 2 key invariants, the alpha invariant IS and the delta invariant NEX.
Alpha and delta invariants. Sounds pretty technical. Can you give us a basic idea of how they're used?
They establish lower bounds for K-stability. The specifics get complicated, but by analyzing these bounds, the paper shows the connections between pointless varieties, Kähler-Einstein metrics, and K-stability.
So it's all about manipulating and analyzing these invariants to uncover the hidden geometric truths. And the paper doesn't just stop at abstract theorems, does it?
No, it gives concrete examples to illustrate these concepts. Section 6 of the paper is full of examples of pointless Fano threefolds constructed in various ways.
Let's look at some of those examples, any that stand out.
Examples 6.1, 6.2, and 6.5 offer some cool constructions over the rational numbers and the real numbers. Let's start with 6.1.
Sounds good.
Example 6.1 describes a pointless Q-form V of a 5-dimensional homogeneous space, specifically G2P, where G2 is an exceptional algebraic group.
5-dimensional homogeneous spaces, exceptional algebraic groups. I'm a bit lost. Can you break that down?
Think of this homogeneous space as a space with lots of symmetry, and G2 as a special group with unique properties. The key is that this space V has no rational points, making it a pointless variety.
Okay, so we have the special symmetrical pointless space. What happens next?
The paper then shows how to construct a pointless Q-form of a smooth Fano threefold from the space V, which happens to be in family or 1.9, one of the families we talked about.
So we're using this unusual five-dimensional space to create a specific type of pointless Fano threefold. What about example 6.2?
Example 6.2 takes us to the real numbers. It highlights a whole family of smooth Fano threefolds defined over the real numbers that are pointless and have smooth complex models in family E1.0.
A whole family of real pointless Fano threefolds. And lastly, what about example 6.5?
Example 6.5 dives into explicit constructions of real pointless smooth Fano threefolds whose complex models belong to family 2.12, another one of those families with special properties.
Got it. These examples show that these concepts aren't just theoretical. We can actually build these pointless varieties.
Exactly. And those are just a few examples from the paper. There are many more, each offering a unique glimpse into the world of pointless Fano varieties and their connections.
Now, these examples mainly focus on Fano threefolds. What happens in even higher dimensions?
That's where it gets really exciting. Exploring pointless varieties and case stability in higher dimensions is a vast, uncharted territory. It's ripe for discovery, full of potential for new theorems, mind-bending constructions, and maybe even a few more surprises.
My brain's already feeling the strain, but that's what makes the deep dive so exciting. We've gone from simple pointless varieties to a world of intricate geometry, special metrics, and advanced invariants. What are some key takeaways from all this?
I think the most important takeaway is that the absence of something like rational points can be incredibly revealing. It can hint at hidden structures and deep connections in mathematics.
Like those optical illusions where you see the image by focusing on the empty space. And while we've covered a lot, I feel like we've only just scratched the surface. So many unanswered questions, so many paths to explore.
Absolutely. We've laid a good foundation, but there's a whole universe of pointless varieties in higher dimensions waiting to be discovered. Who knows what fascinating connections and surprising results are out there?
Well, on that tantalizing note, we'll wrap up part 1 of our deep dive into pointless Fano varieties. Join us next time as we delve deeper into the details of these theorems and proofs, unpacking the logic and beauty of these mathematical concepts. Thanks for diving deep with us today.
Welcome back to our deep dive into pointless Fano varieties.
My brain is still buzzing from our last session. We went through so much, from Del Pezzo surfaces to case stability and those 8 exceptional Fano threefold cases. It's crazy how the lack of something as simple as a rational point can lead to such deep and beautiful math.
It really is. Today we're going to dig into some of the proof techniques used to show those connections we talked about.
Sounds good to me. Ready to get into some serious math. Where do we start?
Let's go back to section 3 of the paper where they focus on Del Pezzo surfaces, those two-dimensional Fano varieties.
Right, and the paper shows that pointless Pezzo surfaces with quotient singularities always have Kähler-Einstein metrics.
Exactly. And the proof relies a lot on understanding the alpha invariant NS, which tells us how singular a pair can be while still being log canonical.
Okay, hold on. Log canonical, remind me about that one.
Log canonical describes how bad singularities are in algebraic geometry. It's a bit technical, but basically a log canonical singularity is mild enough that certain tools and theorems still work.
Got it. So the alpha invariant tells us how much we can push the singularities of a surface before they get too crazy.
Right. And lemma 3.1 in the paper is key. It says that for a pointless Del Pezzo surface S without S less than 12, there's a special geometrically irreducible curve C on the surface.
What's so special about this curve C?
This curve C is closely tied to the alpha invariant. The negative of the canonical divisor of S at Ks is numerically equivalent to 1S times C plus some effective Q divisor.
Lots of symbols there. What's the geometric idea?
Basically, this means the curve C captures a lot of information about the singularities of the surface. The smaller the alpha invariant, the bigger the coefficient in front of C, which means more severe singularities.
And this connection between the curve C and the alpha invariant is important for the proof.
Absolutely. The proof looks closely at the properties of this curve C. Like lemma 3.3 shows that if the surface S is pointless and the beta invariant of C is non-negative, then the self-intersection of CC must be positive or 0.
Wait, another invariant. What's the beta invariant all about?
The beta invariant measures how the curve C contributes to the overall instability of the surface. If it's non-negative, it means C isn't causing too much trouble.
So if the surface is pointless and the curve isn't a big source of instability, then it has to have specific geometric properties. Its self-intersection can't be negative.
You got it. And the paper goes on to establish a bunch of results using similar logic. They look at different cases based on the Picard rank of the surface, the properties of the curve C, and the relationship between the alpha and beta invariants.
Okay, so it's a lot of careful case analysis using these invariants to narrow down the possibilities and ultimately prove that pointless del Pezzo surfaces with quotient singularities always have Kähler-Einstein metrics.
Exactly. They squeeze the problem from all angles using these geometric tools to show there's no way for pointless surfaces to avoid having a Kähler-Einstein metric.
Impressive. But we've been talking about surfaces. What about Fano threefolds? They're more complicated, right?
They are. In Section 5, the paper tackles the case stability of pointless Fano threefolds, and the proof strategy changes a bit.
What's the main difference?
The alpha invariant is still there, but the focus shifts to the delta invariant, which gives a more global measure of case stability for Fano varieties.
So instead of individual curves and singularities, we're looking at the overall stability of the threefold.
Right. And a key tool is the valuative criterion for case stability. This basically says that a Fano variety is K-polystable, a strong form of case stability if and only if its delta invariant is strictly greater than 1.
So if we can show that the delta invariant of a pointless Fano threefold is greater than 1 we've shown, it's K-polystable.
Exactly. And that's how Section 5 approaches it. They look at different families of pointless Fano threefolds and carefully calculate lower bounds for their delta invariants.
Sounds like a lot of tough calculations.
It is. They use all sorts of techniques, including the Abans-Wang method, which lets them estimate the delta invariant by studying how certain divisors intersect curves and surfaces within the threefold.
So it's all about carefully breaking down the geometry of the threefold and using that to establish the bounds for the delta invariant.
Precisely. And through these calculations, they prove that many families of pointless Fano threefolds are in fact K-polystable, which strengthens the link between the lack of rational points and the potential for Kähler-Einstein metrics.
Okay, I'm starting to see how geometry and algebra are working together here. It's fascinating how these abstract ideas and calculations reveal truths about the structure of these varieties.
It's a beautiful interplay. To dig a little deeper, let's look at Proposition 5.1, which deals with Fano threefolds that have a conic bundle structure.
Conic bundle structure, huh? Can you explain that?
Imagine you have a three-dimensional space, and over each point in a certain two-dimensional surface, you have a curve defined by a quadratic equation. This collection of conics bundled together over the surface is a conic bundle structure.
So, like a family of conics parameterized by a surface, how does this relate to pointless Fano threefolds?
Well, Proposition 5.1 says that if you have a smooth, pointless Fano threefold X with a conic bundle structure over a surface S, then the Picard number of X is greater than or equal to the Picard number of S plus 1.
Okay, hang on. What's the Picard number again?
The Picard number basically measures how complex the divisors on a variety are, how many independent divisors there are.
So this proposition is saying that if a pointless Fano threefold has this conic bundle structure, then its complexity in terms of divisors is at least a bit greater than the surface it's bundled over.
Right. And this is important for proving the case stability of these varieties.
How so?
The proof looks at a specific divisor on the threefold, the one associated with the conic bundle structure. They show that this divisor has to be big, meaning it covers a large part of the threefold's volume.
So this big divisor tied to the conic bundle structure helps us understand the threefold's geometry.
Exactly. And this, combined with other geometric arguments, lets them establish a lower bound for the delta invariant of these Fano threefolds.
Interesting. So even though we're looking at pointless varieties without rational points, having certain geometric structures like these conic bundles helps us analyze their case stability and maybe even their ability to have Kähler-Einstein metrics.
Exactly. It shows how different geometric ideas can work together to help us understand even the most abstract and seemingly empty spaces.
This is all really cool, but I have to admit my brain is getting a bit overloaded with all these details. Can we step back and look at the big picture? Why should we care about pointless Fano varieties in the first place?
That's a great question. It's easy to get caught up in the technical stuff, but we should remember why we're exploring these things.
Right. What's the big deal about these varieties? Why are mathematicians so interested in them?
Well, for one thing, Fano varieties are super important in algebraic geometry. They have a rich and complex structure, and understanding them is key for solving many other problems in the field.
Okay, so they're important on their own. But what about the pointless part? What makes that so special?
The pointless aspect might seem strange at first. I mean, how can we study something with no points? But as we've seen, not having rational points actually tells us a lot about the geometry of these varieties.
It's like those optical illusions we talked about earlier. Sometimes what's not there is just as important as what is there.
Exactly. And for Fano varieties, not having rational points leads us to these connections with Kähler-Einstein metrics and case stability.
So by studying these pointless varieties, we're learning about some of the most basic and fundamental ideas in geometry.
Precisely. And as we move into higher dimensions, who knows what other connections and surprising things we might find?
That's what makes this so exciting. It feels like we're on the edge of something really big. But for now, I think we need to give our brains a break.
Agreed. Let's continue this conversation next time, and we'll look at those concrete examples and see how these concepts work in specific cases.
Sounds good. I'm excited to see what else we can find in this paper. Welcome back to the deep dive. We're wrapping up our look at pointless finito varieties, and I'm really interested in those concrete examples we mentioned last time.
Let's get right to it. Remember, these examples really show the connections between pointless varieties, case stability, and those Kähler-Einstein metrics.
Right. We were talking about how the paper actually constructs specific pointless finito threefolds within different families.
Exactly. Each example highlights something unique about the theory. Let's start with example 6.1, which focuses on a variety in Familia 1.9.
Okay. Refresh my memory. What's so special about Familia 1.9?
Family 1.9 is all about Fano threefolds whose complex models can be embedded in Pezzo, and in this example they build a pointless Q-form, which means it's defined over the rational numbers and doesn't have rational points.
Okay. A specific kind of pointless Fano threefold in this family. How do they construct it?
They start with a 5-dimensional homogeneous space G2P, where G2 is an exceptional algebraic group and P is a maximal parabolic subgroup.
Homogeneous spaces, exceptional groups.
Oh.
It's getting pretty abstract.
It is, but the key is that this space, they call it V in the paper, is a G2 torsor defined by a special element in Milnor K theory. And importantly, it's pointless over the rational numbers.
So we have this special 5-dimensional V without rational points. How do we get a 3-dimensional Fano variety for that?
They use the fact that V can be embedded in a K form of Pugh, which they call U. They take the intersection of V with 2 specific divisors in U, and that creates a 3-dimensional variety X.
Like cutting a 3-dimensional slice out of this 5-dimensional space.
Exactly. And this X inherits the pointlessness from V, so it also has no rational points. Plus, because of how it's built, it belongs to family 1.9, its complex model can be embedded in Pezzo.
That's a really neat construction, using higher dimensional spaces to make these special pointless Fano threefolds. How about example 6.2? That one took us to real numbers, right?
Yeah. Example 6.2 is about family 1.Pezzo, and this time it's a bit simpler. The paper mentions a result that guarantees a whole family of smooth Fano threefolds exists over the real numbers. These threefolds are pointless, and their smooth, complex models belong to family O 1.10.
So no complex construction from higher dimensions this time. They just say this family of real pointless Fano threefolds exists.
Right. The focus here is on them existing, not the specific construction.
Makes sense. What about example 6.5?
Example 6.5 goes back to specific constructions, but this time for family 2.1, which is Fano threefolds whose complex models come from blowing up pay along certain curves.
I love blowups. How do they create pointless Fano threefolds in this family?
The paper cites another paper that shows how to construct real, pointless, smooth Fano threefolds in this family, but they don't go into the details here.
Cliffhanger. But it's still cool knowing these constructions exist. What are some takeaways from these examples?
These examples really show how diverse and rich the world of pointless Fano varieties is. They can be constructed in so many ways using tools from higher dimensional geometry-specific family properties and even in different fields like the real numbers.
It shows how deep and complex this research area is. We've seen how not having rational points leads to surprising links with other geometric ideas like case stability and Kähler-Einstein metrics. It's like these empty spaces actually have a lot of hidden structure just waiting to be discovered.
That's a great way to put it. And as we learn more, who knows what other surprises we'll find? Exploring pointless Fano varieties in higher dimensions is a huge open area with tons of potential for new discoveries and insights.
This has been an amazing journey, and I feel like we've only scratched the surface. I can't wait to dig into the next paper on my stack.
Me too. There's always something new to discover in math.
On that note, we'll wrap up our deep dive into pointless Fano varieties. To our listeners, we encourage you to keep exploring, keep asking questions, and keep diving deep into this fascinating world of mathematics. Thanks for joining us on this adventure. Welcome back to the show, everyone. It's time for another deep dive, and this time we're wading into some pretty deep mathematical waters.
Deep waters indeed.
You know how this works, right? We take a whole pile of research and extract the really interesting bits. And today, we're focusing on K-stability and how it relates to the existence of rational points on Fano varieties.
It's a fascinating area, even for, experienced mathematicians. So buckle up, because we're about to go on a wild ride.
Yeah, this is going to be fun. Okay, so right off the bat, we're talking about a connection between geometry and arithmetic, which already sounds pretty mind-blowing. K-stability, which is this geometric concept, might actually help us predict whether or not a Fano variety has rational points. Can we start by just making sure we're all on the same page? What exactly are Fano varieties and rational points?
Absolutely. So picture an algebraic variety, which is basically a geometric object defined by polynomial equations.
Yeah, I'm picturing...
Now, a Fano variety has this special property related to its curvature. You can almost think of it as having a certain roundness to it, similar to how a sphere has positive curvature.
All right, so like a sphere-like variety.
Yeah.
Got it. Now, what about rational points?
Well, a rational point on our variety has coordinates that can be expressed as fractions.
So simple fractions like 1/2 or 3/4.
Exactly. And any point with irrational coordinates, like pi or the square root of 2, wouldn't be considered a rational point.
Okay, that makes sense. So we're looking for those points with nice, clean fraction coordinates. Now, where does this whole idea of K-stability fit into this picture?
That's where things get really interesting. K-stability helps us figure out if a Fano variety has something called a Kähler-Einstein metric. Think of it like a special way to measure distances on the variety.
So a metric, like a ruler for our Fano variety.
Yeah, exactly. And it gives us this really powerful tool to understand the variety's geometric structure.
So it's all about understanding the shape and structure of these Fano varieties. And the big question is, does having a Kähler-Einstein metric or not having one tell us anything about whether or not the Fano variety has those rational points?
You got it. That's the central question that mathematicians are trying to answer. It's all about connecting the geometry of the metric to the arithmetic of the rational points.
Wow, that's a pretty deep connection. How do mathematicians even begin to approach a question like that?
Well, one way is to start with simpler cases, and that's exactly what one of our sources does. They dive into the world of two-dimensional Fano varieties, which are also known as del Pezzo surfaces.
So they're looking at a kind of simplified two-dimensional version of these Fano varieties.
Exactly. And they focus specifically on del Pezzo surfaces that are defined over a subfield of the complex numbers. What they found is pretty remarkable. If a smooth del Pezzo surface defined over such a subfield doesn't have any rational points, then its geometric model, its representation in complex space, so to speak, actually admits a Kähler-Einstein metric.
So no rational points seem to guarantee a Kähler-Einstein metric in this two-dimensional case. That's a pretty strong connection. But does this hold true as we move into higher dimensions?
That's the million-dollar question. And the answer, unfortunately, is not so straightforward. When we move to three-dimensional Fano varieties, or Fano threefolds as they're often called, things get a lot more complicated.
So the neat connection we saw in 2 dimensions might start to break down as we go up in dimension.
Exactly. The source gives some examples to illustrate this complexity. For instance, imagine taking a threefold that's formed by the product of a conic without rational points and a del Pezzo surface, either F1 or S7. These threefolds don't have Kähler-Einstein metrics, but they also don't have rational points.
So these examples are like, wait a minute, a missing Kähler-Einstein metric doesn't automatically mean we have rational points.
Right. It throws a bit of a wrench into things. But don't worry, mathematicians are clever. They came up with another theorem, let's call it theorem B, for now, to shed some light on this whole higher dimensional puzzle.
Oh, a new theorem. I'm intrigued. Tell me more about theorem B.
Okay, so theorem B essentially states that if you have a smooth Fano threefold defined over a subfield of the complex numbers, and it doesn't have rational points, and its geometric model isn't Kähler-Einstein, then it has to fall into one of a few very specific exceptional cases.
All right, so it's like a yes unless kind of situation. What are these exceptional cases like?
Well, some are pretty straightforward, like those products we just talked about, the ones with a pointless conic and a del Pezzo surface, either F1 or S7. But then there are 8 other more intricate cases that involve something called blow-ups of certain geometric objects.
Hold on, blow-ups. What are those?
So in geometry, a blow-up is a way to modify a variety by essentially replacing a point with a copy of projective space. It's a pretty powerful tool that mathematicians use to analyze the structure of varieties.
Interesting. So we have these 8 complex blow-up cases that are like exceptions to the rule. But does Theorem B tell us anything else about these exceptional cases?
Here's where it gets even more interesting. The source points out that all of these exceptional cases are actually K-unstable, and this leads to a pretty fascinating consequence, which they call Corollary 1.1.
Okay, a corollary. Hit me with it.
Corollary 1.1 states that if the geometric model of a smooth Fano threefold is strictly K-semistable, then it must have a rational point.
Wait, back up a second. So if a Fano threefold is K-stable, it might or might not have rational points. But if it's in the strictly K-semistable middle ground, it's guaranteed to have rational points.
Exactly. That's the key takeaway here. This middle ground of stability, for whatever reason, forces the existence of those rational points.
Wow. This whole K-stability thing is turning out to be way more than just a geometric curiosity. It's like this hidden key to understanding rational points on Fano varieties.
You said it.
But how do mathematicians even prove these theorems and corollaries? What kind of tools are they using?
That's a great question. The source does touch upon the strategies they use, but it does get a bit technical.
Don't worry, we're not afraid of getting a little technical here.
All right. Well, one of the key concepts they use is something called the delta invariant, which basically measures how singular or non-smooth a point on a variety is.
So like how pointy a point is.
Haha, yeah, you could think of it that way. And this delta invariant is closely linked to the K-stability of the variety. They also use other powerful tools from algebraic geometry, like the minimal model program, which helps simplify the study of varieties, and various techniques for analyzing how varieties intersect.
So we're talking about some pretty sophisticated mathematical machinery here, but can you give us an example of how all of these techniques play out in practice?
Of course. The source actually provides several examples of pointless, smooth Fano threefolds, meaning those that don't have any rational points.
Oh, so they're showing how all of this theoretical stuff actually applies to concrete examples.
Exactly. One example they give is a pointless Q form of a smooth Fano threefold that belongs to something called family 1.9. They label it as example 6.1 in the source material.
Okay, a Q form, just a quick reminder, what exactly does that mean again?
Sure. A Q form of a variety is essentially a way to represent that variety using equations with coefficients that are rational numbers. So in this case, they found a way to describe a smooth Fano threefold from family 1.9 using equations where all the coefficients are nice, clean fractions.
Okay. So they found this specific way to represent this Fano threefold using rational numbers, and it turns out that this particular representation has no rational points at all.
You got it.
That seems counterintuitive.
Mm-hmm.
If the variety itself can be described using rational numbers, you'd think it would naturally have at least some rational points.
You'd think so, right? But this just goes to show that things aren't always so straightforward. The geometry of these Fano threefolds can be pretty subtle, and the existence of rational points can depend on very specific properties of how they're represented.
This is getting pretty mind-bending, but I'm starting to see the depth and complexity of this whole area of research.
It's definitely a deep dive.
Okay, so they've given us one example. What other families or examples do they explore?
Well, they also highlight an example from family 01.10. This family is interesting because it contains smooth Fano threefolds that, when they're defined over the real numbers, actually don't have any real rational points.
Hold on, so these Fano threefolds are happily existing in the world of real numbers, but none of their points have coordinates that are real numbers. That seems even more paradoxical.
It is pretty counterintuitive. But to understand why this happens, we need to remember that real numbers can be either rational, meaning they can be expressed as fractions, or irrational, meaning they can't be expressed as fractions.
Right, like pi or the square root of 2, classic examples of irrational numbers.
Exactly. So imagine you have a Fano threefold that's defined over the real numbers. It's possible that the geometry of this Fano threefold somehow forces all of its points to have at least one coordinate that's irrational. In other words, the shape of the Fano threefold might prevent it from having any points where all 3 coordinates are nice, clean fractions.
I'm trying to visualize this. It's like the Fano threefold is curved in such a way that it just can't land on any points with purely rational coordinates, even though it's living within the space of real numbers.
That's a really good way to think about it. The geometry of the Fano threefold creates these constraints that just make real rational points impossible.
This discussion is really highlighting how intertwined geometry and arithmetic are.
Yeah, they're like two sides of the same coin. You can't really understand one without the other.
Absolutely. And it's fascinating to see how this plays out in the realm of Fano varieties and case stability.
And we've only just begun to scratch the surface.
I'm ready to keep digging. What other families or examples should we be looking at?
Well, there's one example from the source material that focuses on a smooth Fano threefold, let's call it X, with Picard rank 1. The effective cone is generated by an ample divisor H such that KXXRH for some positive integer R. This integer R is called the index of X. We are particularly interested in Fano threefolds of index 1.
Okay, I'm following so far. Can you tell me about the families of these Fano threefolds?
The family of Fano threefolds of index 1 is completely classified. There are 17 deformation families, which can be divided into 105 deformation types.
Wow, 105. How do we know that?
Well, for every smooth Fano threefold X of index 1, we know that pic X equals ZH, where H is the ample generator of pic X. We also know that hec X, OXH plus 2, and H rho be 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 30, 40.
That's a lot to unpack. Maybe we can look at specific cases to help understand all this.
Sounds good. Let's look at smooth Fano threefold and family 1.9.
All right, so zooming in on one family out of 105, what makes family 1.9 special?
It's interesting because this family includes examples of Fano threefolds that don't have any rational points. The source actually provides a specific example of a pointless Q form of a smooth Fano threefold in family O1.9, which they label as example 6.1.
Wait, a Q form? Remind me what that means again.
Sure. A Q form of a variety is just a way to represent that variety using equations with coefficients that are rational numbers. In this example, they found a way to describe a smooth Fano threefold from family O1.9 using equations where all the coefficients are simple fractions.
Okay, I remember now. So they found a specific way to describe this Fano threefold using rational numbers. And it turns out that this specific representation has no rational points.
Exactly. It's like they've positioned this Fano threefold so that none of its points have coordinates that can be written as fractions.
That seems so strange. You would think that if the variety itself can be described using rational numbers, then it would naturally have some points with rational coordinates.
It's definitely counterintuitive, but that's what makes this whole area of research so fascinating. The geometry of these Fano threefolds is much more subtle than we might initially think.
So this example shows that things aren't always straightforward. The existence of rational points can depend on very specific choices about how the Fano threefold is described.
Exactly, and that's why mathematicians are so interested in exploring these different families and examples. They're trying to uncover the hidden connections between the geometry and arithmetic of these objects.
Okay, so family OR 1.9 has given us some food for thought. What other families or examples do we have?
Well, there's another interesting example from family OR 1.0. This family is special because it contains Fano threefolds that, when defined over the real numbers, don't have any real rational points.
Wait, so these Fano threefolds exist in the world of real numbers, but they don't have any points whose coordinates are real numbers. That seems even more paradoxical.
I know, it's pretty mind-bending. To understand why this can happen, we need to remember that real numbers can be either rational, expressible as a fraction, or irrational, not expressible as a fraction.
Right, I remember that. Pi and the square root of 2 are classic examples of irrational numbers.
Exactly. So imagine you have a Fano threefold that's defined over the real numbers. It's possible that its geometry forces all of its points to have at least one coordinate that's irrational. The shape of the Fano threefold might prevent it from having any points where all three coordinates are nice, clean fractions.
I'm trying to picture that in my head. It's like the Fano threefold is curved in such a way that it just can't land on any points with purely rational coordinates, even though it exists within the space of real numbers.
That's a great way to think about it. The geometry of the Fano threefold might create constraints that just make real rational points impossible.
This is blowing my mind a little bit.
It's definitely one of those things that takes a bit of time to wrap your head around, but it's a testament to the incredible richness and depth of mathematics.
All right, so we've seen how families OS 1.9 and O1.10 provide examples of Fano threefolds that defy our expectations about rational points. What else can you tell me about these families?
Well, both of these families are part of a much larger classification of Fano threefolds. There are actually 105 different types, each with its unique properties and characteristics.
105 different types.
Yeah.
Wow. That's a lot of Fano threefolds to explore.
It is, and mathematicians are still actively studying these different types, trying to uncover all their secrets. The search for pointless Fano threefolds is a big part of that research effort.
I'm starting to see why mathematicians find this area so fascinating. It's a mix of geometry, arithmetic, and a bit of detective work all rolled into one.
Exactly. And as we continue our deep dive, we're going to delve even deeper into the techniques and methods they use to uncover these hidden connections between K-stability and rational points.
I'm ready to keep exploring. What should we focus on next?
Well, next we can dive into the proof of Theorem B. It's quite intricate, but I think we can break it down in a way that makes sense.
Sounds good to me. Let's do it.
Okay, so let's jump into the proof of Theorem B. Now remember, we're dealing with Fano threefolds here, which are three-dimensional. And as you might expect, things get a lot more complex when we move from 2 dimensions to 3 dimensions.
More dimensions, more problems, right?
Pretty much. So to tackle this proof, the source material breaks it down into a bunch of different cases, kind of like a detective solving a mystery one clue at a time.
Okay, a multi-layered detective story. I like it. Can we walk through one of these cases to see how it all works?
Absolutely. Let's take a look at the case where our Fano threefold, let's call it X, has Picard rank 1.
Picard rank 1. Remind me what that means again.
Sure. The Picard rank essentially tells us how many independent directions we can move on our variety. So Picard rank of 1 means our Fano threefold is pretty rigid, geometrically speaking. Doesn't have a lot of wiggle room.
Got it. So we're dealing with a Fano threefold that's kind of stuck in its ways.
Mm-hmm.
What else can you tell me about X?
Well, in this case, the effective cone of X, which represents all the possible divisors on X, is generated by an ample divisor H. And we know that entry X, RH, where R is some positive integer. This integer R is called the index of X.
Okay, so we've got this ample divisor H generating the effective cone, and we've got this index R that's related to the canonical divisor KX. What's so important about the index R?
The index of a Fano threefold is a really important invariant. It tells us a lot about the geometry of the variety. In this particular case, we're interested in Fano threefolds of index 1. That means the Fano threefolds where an3 is ample.
So we're zeroing in on a very specific type of Fano threefold here, one with Picard rank 1 and index 1. Why are these properties so important for proving Theorem B?
Well, these specific properties let mathematicians use some really powerful tools and techniques from algebraic geometry. You see, Fano threefolds of index 1 have been studied extensively, and their classification is well understood.
Ah, so we're not starting from scratch here. We can build upon the existing knowledge about these Fano threefolds. What can you tell me about their classification?
It turns out that the family of Fano threefolds of index 1 is completely classified. There are 17 deformation families, which are further divided into 105 deformation types.
105 different types of Fano threefolds of index 1. That's still a lot. How do mathematicians even keep track of all of them?
It's a testament to the power of algebraic geometry. Mathematicians have developed sophisticated methods for classifying these varieties based on their geometric properties. They look at things like the degree of the Fano threefold, which is related to the self-intersection number of the ample divisor H, and the Hodge numbers, which are these subtle invariants that capture information about the complex geometry of the variety.
So it's like they're giving each Fano threefold a unique fingerprint based on its geometric features.
Exactly. And then they group them together based on similarities in their fingerprints. This classification is a huge achievement because it allows mathematicians to study these objects in a systematic way.
Okay, so knowing that these Fano threefolds of index 1 are completely classified, how does that help us prove Theorem B in this specific case?
It makes things a lot simpler. Instead of dealing with an infinite number of possibilities, we now have a finite set of 105 different types to consider.
So it's like narrowing down the search from an entire library to just one bookshelf.
Exactly. And for each of those 105 types, mathematicians can carefully analyze its properties and figure out if it satisfies the conditions of Theorem B.
So they go through each shape one by one and check if it fits the criteria.
Precisely. And that's where that delta invariant we talked about earlier comes in handy.
Ah, right, the delta invariant, that measure of how pointy a point is.
Yeah, exactly. For each of those 105 deformation types, mathematicians can use various techniques to estimate its delta invariant, and that helps them establish lower bounds on something called the stability threshold of the corresponding Fano threefold.
Hold on, the stability threshold. Can you remind me what that is again?
Sure. The stability threshold basically tells us how much we can perturb or deform the geometry of a Fano threefold before it loses its case stability. A higher stability threshold means the Fano threefold is more robust. It can withstand more deformation without falling apart, so to speak.
Okay, so a high stability threshold means the Fano threefold is tougher, less likely to crack under pressure.
That's a great way to put it. And the delta invariant gives us a way to estimate this stability threshold. By understanding the singularities of a Fano threefold, we can get a sense of how stable it is.
So it's like knowing the weak points of a structure helps us understand how much stress it can handle.
Exactly. And what mathematicians have found is that a lot of these Fano threefolds of index 1 actually have stability thresholds that are greater than 1, so they're quite robust.
Okay, so they can handle a lot of geometric deformation without losing their K-stability. But how does that help us prove Theorem B?
Here's the key connection. The source material demonstrates that if a Fano threefold has a stability threshold greater than 1, and it's defined over a subfield of the complex numbers, then it must have rational points.
Wait, so having a high stability threshold forces the existence of rational points. Why is that?
The proof of that connection gets pretty technical. It delves into the relationship between the stability of a Fano threefold and its arithmetic properties. But the main idea is that a high stability threshold puts limits on how a Fano threefold can be embedded into projective space. And those limits, in turn, force the existence of rational points.
Okay, I'm following the general idea, even if the technical details are a bit over my head. But it sounds like we're starting to see this really deep connection between the geometry of these Fano threefolds and their arithmetic properties. The way they're situated in space influences whether or not they have those special fraction points.
You're getting it. And this is just one example of how the proof of Theorem B unfolds. By carefully examining lots of different cases using the classification of Fano threefolds and employing tools like the delta invariant and the stability threshold, mathematicians have been able to establish this really remarkable link between K-stability and the existence of rational points.
It's a pretty amazing feat of mathematical reasoning. I'm starting to see the big picture here, but I have to admit my brain is still a bit fuzzy on some of the details. Do you think we can maybe look at a concrete example of a Fano threefold of index 1, just to make things a little more tangible?
Absolutely. Let's take a look at a classic example. The cubic hypersurface in projective force space.
Okay, a cubic hypersurface. Remind me what exactly that is.
Sure. So a hypersurface is basically just a subvariety of projective space that has one less dimension than the ambient space. So in a projective force space, which has 4 dimensions, a hypersurface would have 3 dimensions. And a cubic hypersurface is a hypersurface that's defined by a single homogeneous polynomial equation of degree 3.
All right, so we're talking about a 3-dimensional object sitting inside a 4-dimensional space, and it's defined by an equation where all the terms have a total degree of 3. What makes this cubic hypersurface a Fano threefold of index 1?
Well, it turns out that if you have a smooth cubic hypersurface in projective force space, it automatically satisfies the properties of being Fano and having index 1. It's a really nice example of how a relatively simple algebraic description can lead to a geometric object with some really interesting properties.
I'm intrigued. What can you tell me about the geometry and the arithmetic of this cubic hypersurface?
Well, the cubic hypersurface has a very rich geometry that mathematicians have been studying for a long time. It's known to be a rational variety, which means that it can be parametrized by rational functions. And that implies that it actually has an infinite number of rational points.
Ah, so our cubic hypersurface fits in nicely with Theorem B. It has a high stability threshold, and it also has rational points.
Exactly. And this example shows how we can use Theorem B to gain insights into the existence of rational points on specific Fano threefolds.
This is helping me understand how all these abstract concepts actually play out in real examples. But before we move on, can we circle back to those exceptional cases you mentioned earlier? The ones where a Fano threefold might not have rational points, even if it's not K-stable.
Absolutely. Those exceptional cases are really important because they show that the relationship between K-stability and rational points isn't always a simple yes or no. There are these subtle geometric configurations that can throw a wrench into things.
Okay, I'm ready to hear about these rule breakers. What makes them so special?
All right, so these exceptional cases, they're kind of like the rebels of the Fano threefold world.
Rebels. I like it.
Yeah.
So tell me more about these rebels. What makes them so unique?
Well, they show us that even if a Fano threefold isn't K-stable, it might still not have any rational points. It's not a simple rule.
So they're like, hey, we don't follow your rules.
Exactly. And they remind us that there's still a lot we don't understand about the geometry of these objects. Remember those blow-up cases we mentioned before? Those are a perfect example of exceptional cases.
Right. The ones where you're essentially replacing points with projective spaces. How do blow-ups create these exceptional cases?
Blow-ups can really shake things up geometrically. They can introduce new curves and surfaces, change how things intersect, and even affect the overall topology of the Fano threefold. And sometimes those changes lead to the disappearance of rational points.
So blow-ups can reshape the Fano threefold in a way that gets rid of those fraction points.
That's a great way to put it. And the source material goes into detail about several specific blow-up scenarios that create these exceptional cases. One example involves blowing up a smooth quadric threefold along a certain type of curve.
Okay, a smooth quadric threefold. Can you remind me what that is again?
Sure. A quadric threefold is just another type of three-dimensional variety. It's defined by a quadratic polynomial equation. It's a pretty basic object in algebraic geometry.
All right, so we're taking this relatively simple quadric threefold, blowing it up along a specific curve, and somehow that can get rid of rational points.
Exactly. It all comes down to the specific curve you choose and how you perform the blow-up. Those are the key factors that determine whether or not the rational points survive.
This is starting to feel like a very delicate operation, like one wrong move and everything falls apart.
It's a good analogy. The geometry of these Fano threefolds is quite delicate, and even small changes can have a big impact on whether or not they have rational points.
All right, let's get specific. Can we walk through a concrete example from the source material to see how this all works?
Of course. Let's take a look at example 6.5, which focuses on a pointless, real smooth Fano threefold. Its geometric models belong to family 2.1.
Okay, so we're focusing on one specific pointless Fano threefold from family 2.12. What's special about family 2.12?
Family 2.12 is a class of Fano threefolds that are created by blowing up projective 3 space along a smooth curve of genus 7 and degree 10. These Fano threefolds have Picard rank 2.
Okay, so we're starting with projective 3 space and blowing it up along a particular curve. What's so special about this curve?
It's a smooth curve of genus 7 and degree 10. The genus of a curve, roughly speaking, measures the number of holes in the curve. A genus of 7 means this curve is pretty intricate, with lots of twists and turns.
Okay, so it's not just a simple circle, it's more complex.
Right, and the degree of a curve in projective space tells us how many points it intersects with a generic hyperplane. A degree of 10 means this curve is embedded in projective space in a pretty complex way.
All right, so we have this twisty curve embedded in projective 3 space. And when we blow up projective 3 space along this curve, we get these Fano threefolds from family 2.12.
Exactly. And the choice of the specific curve is crucial. It's what leads to the existence of those pointless, real smooth Fano threefolds within family 2.12.
So the curve's unique characteristics get passed on to the Fano threefold during the blow-up process, and somehow that leads to the disappearance of rational points.
You got it. The curve's geometry really influences the geometry of the Fano threefold in a big way, and that affects its arithmetic properties.
This example is incredible. It's like a delicate dance between geometry and arithmetic, where small choices can have huge consequences.
I agree. And studying these exceptional cases is so important because they help us understand the subtle interplay between geometry and arithmetic.
It's like these exceptional cases are pushing us to think outside the box and to question our assumptions.
Exactly. They highlight the fact that there's still so much we don't know about these objects, and that's what makes this area of research so exciting.
This has been an amazing journey. We've delved into the world of Fano varieties, explored the deep connections between geometry and arithmetic, and uncovered the surprising role that case stability plays in the existence of rational points. We even encountered those exceptional cases that challenge our understanding and push the boundaries of our knowledge.
It's been a wild ride, and I think it's clear that there's still so much more to discover in this area.
To all our listeners out there, I encourage you to dive into the source material, ponder those open questions, and maybe even contribute to this exciting field of research. Who knows, maybe you'll be the one to make the next breakthrough. Until next time, keep exploring and stay curious.